Hey, good morning.
Hey, Da-Cheng.
How's it going today?
Good, how are you?
Good, good.
Let me make you co-host.
Sure.
Oh, hi, Tisha. Yeah,
Hi,
thanks
Cesar.
for joining us, and
Hello.
hopefully we wouldn't give you any trouble today.
Everything will be very smooth.
Hopefully.
I just made you a co-host as well, Tisha.
Thank you. Okay.
So I'm just going to paste the Zoom info on the VFairs chat announcement now.
So I keep hearing a beeping sound. I do believe that's because the chat message. Should we actually turn the notification off? Otherwise, when we presenting, if someone asking questions, then
Oh no, I think it's actually from VFairs.
Care, I guess. Yeah. That's
oh, okay.
it gets sometimes annoying though.
Hey, Allan. Hey, Cesar.
Can I just try presenting?
Sure, go ahead. We can see the screen, yep.
And you see just the slide, right? Not my speaker notes.
Yep, that's right.
Beautiful. Okay, thank you.
And quick question. Yesterday we decided to insert like a 10-minute break, and one is after the regularizing with synthesized graph, right?
No, it's actually after natural graphs, the Caesar's
Natural
tutorial.
graph. And the second one is after
The adversarial regular.
I see, adversarial learning. Got it.
So it's roughly around the 1 hour and the 2 hour marks.
Should I actually modify the slides, the presentation slides to insert this? I could modify the agenda slide to insert these two breaks. Oh, you don't
Yeah,
think it's
I think that's a good idea. If you have like the slides version just in the copy that you're presenting, maybe
Yeah.
you can just add like a.
Let me do that.
That sounds good. Yeah, thanks.
Is there anywhere, I'm on the VFairs site right now. Is there anywhere in particular I should go to on this site?
So let me paste the link to VFairs chat here. So that's just the chat interface. Hopefully we won't have to monitor that during the course of our presentation, but I mean, we can monitor it now for the next maybe 20, 30 minutes in case people have trouble accessing our Zoom and they're asking questions there. I just pasted the Zoom info for this presentation on the chat interface.
Sorry, did you post a link to the chat somewhere that I'm missing?
Yeah. So it's on the Zoom chat. You must.
On the Zoom. Okay.
Yeah.
Sorry.
Sorry.
Got it.
I feel like, I feel like the audio, at least for me, is really kind of like choppy, I guess. I don't, it might just be my local connection.
Everything works very good for me.
Okay.
Yeah, it's working well for me as well.
Yeah, I hear you guys just fine.
Can I also do a quick like a sharing screen, making sure everyone could see my slides, but without my speaker notes?
Yeah, go ahead.
Yeah, let me do that. So can everyone see the screen now?
I see it, Da-Cheng.
Yeah, without
And,
this.
and this is this is the slides I just modified. I insert to like a 10-minute coffee break.
Nice.
Sounds good. Looks great. Yeah.
Okay, cool. Let me stop sharing.
I think we're just waiting for Phil and Chun-Ta, right? From our team. I made every one of you co-hosts, just so you know.
I'm trying to think if this is my first time attending the like academic like a research conference virtually. I do believe so. If there's no COVID, I will assume every one of us will be in San Diego right now. That's the original plan.
Yeah.
Yeah.
It looks like there are already a couple people who have joined us from outside our team, just so you guys know.
Yep. So the Tisha, who's also a co-host, is a student volunteer for this session.
Hi, Tisha. Thanks for joining us.
Hi, thanks.
Hey, Phil. Welcome. Hey, Alan, are you there? I see.
Yeah, I'm here. Can you see me?
I see two of your. I mean, I see two instances of your name on the participant list. And I remember I had to, so initially I made you co-host, but then I saw a new Allan Heydon, so I thought maybe you rejoined, and so I made you co-host, but now it looks like there are two. I don't know if.
I only joined once.
Is it possible it's like the presentation? I don't know.
I'm not presenting.
So let me.
That other one doesn't have a microphone. Should I leave and come back?
Hey, hi Arjun and team. How's everything?
Hey, Young. Yes. Yeah, everything is good. We're just getting ready to with our session. I think most of our team is here. We're just waiting for one other person.
Hey, hi. So dropping by just to say hi and wishing you all the best for the session. And we retweeted the thing on KDD news as well, so you should see. I added them to it.
Okay, that's great. Thanks so much, Young.
Thank you.
So I mean, rest of the team. So Young is a co-chair for this hands-on tutor, and he's been really helpful in all the logistics and getting us to where we are today. So really appreciate all of his help.
Hey, no problem. Thank you.
All right, I'm gonna try leaving and coming back.
Okay.
See if the other Allan Heydon goes away when I leave.
Sure, I'll see.
Survey says.
No, I mean the other one didn't go away. Let me
When I
just.
left.
No, yeah, I didn't. But you're right, it doesn't have microphone enabled, but let me just withdraw co-host permission from that. Oh, maybe that's why. Oh, no, it's still there. Okay. Seems harmless for now, so I think it's okay.
And also, during each session, should we actually let the participants know if they want to ask questions during the like tutorial or during the presentation? They could just type their questions. Otherwise, we also leave like 1 or 2 minutes, and also there's a coffee break for them to actually unmute themselves to ask questions. Should we also let them know about this?
Yeah, that sounds like a good idea to do. So yeah, basically for each presentation, we'll have like a minute or two at the end for interactive QA, as well as during the breaks. And of course, they can use the chat interface through the course of the presentation, and the rest of the team can monitor questions, and like we can summarize them either at the end of each presentation, or if it's something really important, we can interrupt the speaker.
Sure.
Chun-Ta is here too. Hey, Chun-Ta.
Hey, Arjun, could you also make me as a co-host? All right,
Yes,
cool.
I just
Thanks.
did. Yeah, Alan, I was just able to remove the other idle instance. Just confirming that you're still on the call.
Yeah, you got the right one.
Okay.
That's so weird.
No, I think that just happened to me. Like, were you logged into the Wova app?
Yes.
I see. So I think when you click on the
Oh, not the app on my phone, but on the website I had logged in.
yeah, on the desktop app. That's what I did. So when you open the link that has our session, I think it automatically joins the Zoom call from there.
Oh,
And that's why we
got it. Thanks, Arjun.
sure.
Maybe let me share the slides since we have 5 more minutes and then we are going to start.
Hey team, just so everyone knows, this call is being recorded.
Do we want to start at 9 a.m. sharp or should we wait for 1 or 2 more minutes?
I think we can wait for a couple of minutes. We do have some buffer, so.
Okay. Then maybe let's start around like a 9:02 or something.
Yeah, sounds good because I think this is the first session of the day.
Okay. So good morning, everyone. Welcome to the neurostructural learning tutorial at KDD 2020. We will wait for another few minutes before we start this session. We will wait for another minute and then start this session. Thank you. Okay, let's get started. So good morning, everyone. Welcome to the neurostructural learning tutorial at KDD 2020. Neurostructural learning is a new learning paradigm that leverages structured signals to train neural networks. In today's tutorial, we are going to provide the concepts and hands-on collabs to walk you through the neurostructural learning framework. And here are the tutorial organizers. We have Arjun, Da-Cheng, yes, that's me, Cesar, Chun-Sung, Allan, Chun-Ta, Phil, and George. We are all from Google Research, and we are very happy to have this opportunity to organize and host this tutorial for sharing the neurostructure learning in TensorFlow with all of you. Here's the agenda for today's tutorial. First, we will provide an overview and introduction to neurostructure learning. Then we will talk about the tools and workflow to process the graph data. After that, we will lead 2 hands-on collabs, one for regularizing the training using the natural graphs, and the other is using the synthesized graphs. And in between these 2 labs, we will insert we will have a 10-minute like a coffee tea break. Then we will introduce another hands-on collab to regularize the training using the dynamically constructed adversarial neighbors. And after this adversarial learning, we will have another 10-minute coffee tea break. And then we will guide you through the neurostructural learning can be used together with TFX to productionize a neural model. And finally, we will talk about some research and future directions and then conclude this tutorial. So in each session, we will leave like 1 or 2 more minutes for you to ask questions. And during the presentation, also feel free to type your questions in the chat, and our teammates will be here to surface your questions. All right, introduction. I'm pretty sure most of you are familiar with the concept of a neural net. Imagine you want to build a neural net for image classification. You will feed a sample. In this case, the sample is an image to the neural net. And then this sample will activate neurons layer by layer and finally make a prediction or a classification on its label. Pretty straightforward. Now let's add a structure into the scenario. Structures usually represent a similarity or relations among samples. And usually the structures cannot be easily represented by features within the sample. And therefore, neural net cannot leverage these structure signals during training. In reality, there are many such structures we can use to better train a neural net. For example, on the left-hand side, we have co-occurrence graphs. In the middle, we have citation graphs. And on the right-hand side, possibly some graphs that we could construct by using the semantic embeddings, such as text embeddings. So you may want to ask, what is the advantage of leveraging structure signals during training? The first one is less label data required for an effective training. As we will show later in the collab, in a lower supervision regime, say we only have, let's say, few or like relatively few label data, the model trained with such structures will have much better performance than the baseline model. And the second advantage is the model robustness. The model trained with structured signals will be more resilient about input perturbations. And also, we will have a collab and results to share with you folks. Ooh. Okay. So I'm pretty sure you have experience in this scenario as well. Say we want to build a model to classify the topic of a document. And we have many, many documents, and it's relatively expensive to hire people reading through each document to provide labels. In this case, the structure can help. The second scenario is the model robustness. And here is the classic example of adversarial images. On the left, we have a panda image. And after adding some malicious perturbations that are usually not detectable by human perception, the model will right now classify the image as the gibbon, basically as the image and label pair showing on the right-hand side. This becomes serious when this adversarial attack is used for sensitive content filtering. So how does the neural structural learning work? At very high level, we want to jointly optimize a neural net with sample features and also with structure. For example, the structure like a graph. And conceptually, we will feed both the feature inputs and also the structure to train the neural net. And mathematically, the structure here is implemented as the regularization term during training. And we call this graph regularization. So as you can see, the loss function is now decomposed into two parts. The first part is called supervised loss. Basically, this term reflects the difference between the prediction and the ground truth. The neural net is trained to minimize this term, so the prediction will be accurate. And the second part is called the neighbor loss. The neighbor loss is calculated based on the projection difference between a sample and its neighbor. Here, let's take the embedding layer as an example. And yes, by saying the embedding layer, we are talking about the second to last layer. So the neighbor loss now represents the distance between a sample's embedding and its neighbor's embedding. So in other words, by minimizing this neighbor loss, we want to encode the local structure into the neural net by forcing a sample's hidden representation and its neighbor's hidden representation close to each other. In addition to this graph regularization, you may also have heard about graph convolution and graph attention, basically all other variants of the graph neural net. But, and yes, you could basically, we treat them as part of the neural structural learning paradigm, and we will also briefly cover this part in the later part of the tutorial. So this is the overall workflow. First, we will combine the training data with the structure to form new training batch. And each training sample right now will be packed with its neighbors. And then we will feed both a sample and its neighbor to the neural net. And then we calculate their corresponding embeddings and use the distance between two embeddings as the regularization term. And here we want to call out that no change will be required on the serving flow. The same model, the same, for example, TensorFlow Lite, same everything. No extra overhead in serving. Everything will happen during training. As we mentioned, this technique is a regularization technique. And the neural structural learning also supports the adversarial learning. So we constructed the adversarial neighbors during training and then use these neighbors as regularization. So this is just a subset here of the tool and libraries we provided in the neural structural learning framework. Please also visit our website to learn more about the tool and APIs in the neural structural learning. In the next section, we are going to talk about the tools and workflow to process the graph data. And here we will pause here for like 1 or 2 minutes to see if anyone has questions.
There's one question on the chat from Mohammed, who's asking, won't there be varying lengths for the inputs since not every sample will have the same number of neighbors?
Okay, that's a really good question. So here we actually provide many options to handle this situation. So for example, we could pack the each sample with dummy neighbors so that the length of basically the number of neighbors for each sample is the same. Or we could also cap, let's say, the maximum neighbors for each sample to have. So basically, in the neural structural learning framework, we support different options to handle the number of neighbors. And there's one more question saying, what is the difference between the neural structure learning and graph convolution neural net? So in graph convolution, we could naturally include the structure and features in a model. So that's a wonderful question. So we will have a more detailed explanation about the graph convolutional neural net in the later part of the and framework. We actually also provide some libraries and tools for you to actually train a graph convolutional neural net. So long story very short, the major difference between the graph regularization and graph convolution is how the neighbor information are aggregated. So as Chang Liang pointed out, in graph convolutional neural net, basically, we could also naturally include the structures and the features of a model. So at high level, in graph convolutional neural net, basically there will be an aggregation phase to aggregate a hidden representation of its sample and also the hidden representation of its neighbor. And these aggregated representation will be used to represent a local neighborhood and then sent to the next hidden layer for downstreaming process. And in the graph regularization, instead of aggregating the hidden representation among a sample and its neighbors, we actually use the difference to tell the neural net actually their hidden representation of a sample and a neighbor needs to be as close as possible. So instead of doing the aggregation, we actually calculate the distance for regularization. So this is the main difference between the graph regularization and graph convolution. And still, we treat like we will show more details later in the later part of this tutorial. We do view all of these techniques are part of the graph neural net variance. So that's a really good question. So there's one more question. Do the structure features? Oh, I saw more questions. So basically, the text is jumping. So let's see.
I can summarize it for you if it's easier.
Okay, cool. Thank you.
First question is, do the structured features have to be a graph? How can I input 3 independent feature columns from a comma separated value file as structured features?
That's a wonderful question. So we are, long story short, stay tuned. In the next section, we will going to talk about how to use our tools and libraries to process the graph data. And but one sentence summary here will be, we do provide a standalone tool to actually parse the CSV file to reading the structure, and then we actually process the structure and save it in a TensorFlow example format.
I just wanted to expand on that. So I don't know if the question was asking if all of if 2 features are completely independent and there's no relation between them, like can they be construed as structured features? The answer is no. So here, when we're talking about structured relations, we're talking about examples that have some relation with each other. So for a given example, if you have like distinct features that are completely independent, I mean, then they would just be treated as regular features, how a regular neural net would consume them.
Cool. Thanks for adding details, Arjun. And the next question is, can this framework be used to new unseen nodes and edges? So, so we will say, basically, the neighborhood here is not necessary to be seen or to be labeled. So basically, we calculate their hidden representation and enforce their hidden representation to be the training samples hidden representation. So so that being said, basically, yes, the framework could be generalized to unseen nodes and edges. And this and Terry also asked, if we have new nodes or edges, do we need to retrain a model? And yes, we do need to retrain a model. Or we could actually we could have a warm start. So we load the pre-trained model and only doing a regularization on these new nodes or edges. Or for example, we could train from scratch. There are different strategies to train with all these like new and unseen nodes and edges. And one more question about the, does this framework take into account about edge weights? Yes, So long story very short, we didn't deep dive into the math equation, but actually each edge weight will determine how important this difference is. So you could imagine if the edge weight is high, then we actually see the neighbor representation need to be very similar to its sample's hidden representation. And therefore, if the distance is too large, then we actually penalize the training heavily by actually having a high like a regularization term. So long story short, yes, the weights are taken into account when designing this graph regularization. So I think we are like running out of time. So one last question here. So by neighborhood, do we say we are doing a pairwise comparison of one sample and all its neighbors, or in both embedding and structure space? Yes, that's right. So by saying neighborhood, we actually we're actually doing a pairwise comparison. So a sample with its first neighbor, the same sample with second neighbor, and things like that. Okay, so I think we are running out of time. So thanks for all the questions. I'm going to pass to Allan for the next session, how to process the graph data.
Okay, I'm going to try and share my presentation. Is it visible to everyone?
Yep.
Okay. Hi, everyone. Thanks for that great NSL introduction, Da-Cheng. My name's Allan Heydon, and during this talk, I'm going to tell you about the NSL tools for pre-processing your data for neural graph learning using graph-based regularization. So I'm going to start from Da-Cheng's end-to-end diagram showing how to do graph-based NSL. At a high level, you can see it can be divided into two parts. So on the left are the steps required for data pre-processing. And on the right is everything for training our model. In this part of the tutorial, I'm going to cover the data pre-processing steps and tools that you'll use to prepare your data for training an NSL model using graph regularization. There are three aspects to that. Let's get to them one by one. So first, we require training examples, at least some of which are labeled. As in fully supervised training, in semi-supervised learning, some of our training examples must have labels, but often it's a small minority of the entire data set, as Da-Cheng mentioned. Second, we require this similarity graph. The weighted edges of this graph denote pairs of similar training instances, and the edge weights denote the degree of similarity. So as Da-Cheng just mentioned, the edge weights are definitely taken into account during training. This graph can take several forms. In some cases, you may already have a natural similarity graph defined on your samples, such as links in a social network or citations between academic papers, or even similarity among examples that are induced by user behavior. In other cases, you'll need to construct a similarity graph based on the degree of similarity between features of your training examples. And I'll be discussing that more later. The third component is we need to combine each of the labeled training samples with its neighbors in the similarity graph. This step produces what I'll call augmented training examples, in which each augmented example includes the features of the labeled example as well as the features of some number of its top neighbors, ranked by decreasing edge weight. In the rest of this talk, I'll be discussing each of these three aspects in more depth. Let's start with the training samples. So the NSL tools assume that training instances, whether labeled or unlabeled, are represented by TensorFlow.example protocol buffers stored sequentially in TensorFlow record files. Each example has to define a string-valued feature containing its globally unique ID, which I refer to as a node ID. These node IDs are used to match the training instances up with the endpoints of each edge in the similarity graph. Labeled examples are distinguished by defining a special feature which contains the label value. Lastly, the NSL toolset requires that labeled and unlabeled examples are stored in separate TF record files. Next, let's talk about constructing the similarity graph. So the NSL tools represent a similarity graph on disk as a tab-separated value or TSV file, where each line of the file has the source ID, the target ID, and optionally the edge weight of the edge. And if you don't specify an edge weight, it defaults to 1.0. NSL also defines some IO helper functions for reading graphs and writing graphs to TSV files. The in-memory representation of a graph is a dictionary of dictionaries, in which the outer dictionary is keyed by the edge's source node ID, and the inner dictionaries map target node IDs to floating point edge weights. So to represent the 4-node graph shown on the right, our outer dictionary has 2 keys, A and C, because those are the only 2 nodes in our graph that have outgoing edges. For the inner dictionary for A, we have 2 entries for B and C, because those are the 2 edges we have from A. And for the inner dictionary for C, we just have 1 entry because there's only 1 edge from C to D. NSL also defines some utility functions for operating on this in-memory graph representation. The add edge function adds a new edge to a graph, while the add undirected edges function makes all the edges in a graph symmetric, essentially by basically adding a reversed copy of every edge in the input. If this reversing process might create 2 edges with the same source and target, the one with the larger edge weight is chosen. As mentioned earlier, you may have a natural organic similarity graph already defined on your training examples, in which case you somehow have to arrange to represent that graph in this simple TSV format. But if you don't have a similarity graph defined, you'll need to build one, and that's what I'm going to cover next. So we also provide a tool in the form of a Python library function that can be invoked as a binary for building a graph based on the features of your labeled and unlabeled training examples. This build graph from config function reads in training samples from 1 or more TF record files and produces a similarity graph in the TSV format that's expected by the downstream tools. It's configured by several different parameters encapsulated by a graph builder config class, which I'll describe more in a minute. But first, I want to just cover how the graph building algorithm works. So the graph builder assumes that every input TensorFlow example proto has a special ID feature and also a special embedding feature. The ID feature has to record the unique string for identifying each instance, which I talked about before. The embedding feature is assumed to capture the essence of each sample. Each embedding is expected to be a dense list of floating point values. All embeddings are expected to have the same number of values or dimensionality, let's call it D. So the algorithm works by comparing the embeddings of all pairs of inputs. The degree of similarity between any 2 samples is computed as the cosine similarity of their embeddings. If you're unfamiliar with the cosine similarity, it's just the cosine of the angle between the embeddings, when each embedding is thought of as a vector in D-dimensional real-valued space, or RD. It can be computed by normalizing both the embeddings so they have unit length and then just taking their dot product. But there's a big problem with this naive approach. It doesn't really scale very well to handle a large number of inputs because it's quadratic. So an input with, say, 100,000 examples would require 10 billion comparisons, which would take too long. So to address that, the graph builder uses a well-known randomization technique called Locality-Sensitive Hashing, or LSH. To describe this approach, I'll work through the following example, which assumes we have 2-dimensional embeddings represented by the 20 points plotted in this diagram here. The first step of the LSH process is to pick some number of random hyperplanes through the origin, which I've denoted by these blue lines in the diagram. These hyperplanes partition the space, and therefore the points, into discrete sections, which we call LSH buckets. We then compare all pairs of points within each bucket. Note that although we have multiple buckets, the number of points in each bucket is expected to be much smaller than our whole input set. So the quadratic nature of the all pairs comparison within each bucket has a much lower impact on performance. The comparisons within each bucket result in some number of intra-bucket graph edges, as shown by the lines in this diagram now. Note that since we never compare 2 points in different LSH buckets, this step never produces cross-bucket edges. But that could be a problem. What if there are 2 points that are actually really close to each other, but they just happened to be split up by a random hyperplane that went right between them? So to address that problem, we just repeat the bucketing process multiple times. On each bucketing round, we pick a different number of random hyperplanes, or a different set of random hyperplanes, I should say, the same number. If we perform enough rounds, the chance of 2 nearby nodes never ending up in the same bucket becomes quite small. So here's our second round. I drew a new set of blue lines. Here are the buckets from our second round of splitting. Note that one LSH bucket has only 1 node, and there's 1 LSH bucket with no nodes at all on the left. And so now again, within each bucket, we look for pairs of nodes that have high cosine similarity, and we draw edges between those. And we can repeat this process any number of times. The more rounds that we perform, the more likely we are to discover all of the edges discovered, as if we had done the all pairs comparison on our entire data set. So as you can tell, this process is configured by several parameters, which are encapsulated in a simple configuration class I mentioned earlier, which is this graph builder config class. First, we have the names of the features in your input examples containing the ID and embedding data. Next is the similarity threshold, which should be a floating point value between 0 and 1. The graph builder creates an edge between 2 nodes if the cosine similarity of their embeddings is at least the value of this threshold. So if you increase the similarity threshold, that will result in fewer but higher quality edges. Next, we have parameters for the number of LSH rounds to perform and the number of LSH splits to do in each round. If the number of splits S is at most the dimensionality of the embeddings, then we may end up with as many as 2 to the S buckets on each round. Lastly, there is a parameter for seeding the number of the random number generator that's used to pick the random hyperplanes. You can make your runs deterministic if you set this value. If you don't set it, if you leave it at Python's none value, then a new random seed is used on each run. So now you may be wondering, what are the performance trade-offs inherent in how the number of LSH rounds and LSH splits are chosen? To illustrate that, I performed multiple runs of the graph builder on a data set containing 50,000 samples, each with a 100-dimensional embedding. I used a value of 0.9 for my similarity threshold. As shown in the graph, when I ran the graph builder on this data set without any LSH splits at all, it took nearly 28 minutes to complete. That actually shouldn't be too surprising. The all pairs comparison involves comparing 2.5 billion embeddings, and each cosine similarity computation requires 200 floating point operations for a total of 500 billion floating point operations. And that's not even counting the upfront work that the library has to do to normalize all the embedding vectors. With a similarity threshold of 0.9, this resulted in just over 35,000 graph edges. The graph shows that if you increase the number of LSH splits, you can reduce the running time dramatically. With 10 LSH splits, the running time is reduced to 45 seconds, which is a speed up of 38 times. As mentioned earlier, we may lose edges the more splits we perform. But as we increase the number of LSH rounds, we discover additional edges. My goal in performing these runs was to find for each value of the LSH splits, the minimal number of LSH rounds that would be required to achieve a recall of at least 99.7% of our original edges. So you might be wondering, how many LSH rounds are needed for each LSH split value? That's shown here in the graph on the right. To achieve our edge recall goal of at least 99.7% with 10 splits required a total of 18 LSH rounds. With that many splits, we expect each LSH bucket to contain roughly 49 nodes. So the total number of expected floating point operations is only 8.9 billion, a more than 50 times reduction compared to the 500 billion floating point operations required when no splits are used. There's one important caveat worth mentioning here though, which I alluded to earlier. which is that as the similarity threshold is reduced, if you make the similarity threshold smaller, the odds of two similar enough points being split by a random hyperplane increases. So for lower thresholds, the number of LSH rounds will have to be increased to achieve high edge recall. In fact, for really low thresholds, the higher the number of splits, the less likely you are to achieve a high edge recall, regardless of the number of rounds you perform. Okay, so that wraps up my discussion of the graph builder. Next, I'm going to talk about the tool for packing each of the labeled examples together with the features of its neighbors. So the pack neighbors tool reads 3 input files: a TF record file that contains the labeled examples, another TF record file containing our unlabeled examples, and a TSV file which has the representation of our similarity graph. It produces a single TF record file with the augmented examples. Note that the neighbors may include either labeled or unlabeled examples, or both, for any given labeled node. As with the graph builder, this tool also has several configuration parameters, which I'm going to describe next. So here are the arguments to the pack neighbors function. The first 4 are the names of the 3 input files and the name of the output file. There's also a Boolean field for specifying whether we want to add the undirected edges to our graph to make it symmetric. If you set this flag to false, which is the default, keep in mind that your pack neighbors will consider only the neighbors of a node X to be the nodes pointed to by X's out edges. There's also a max neighbors parameter. If it's used, that will specify an upper bound on the number of neighbors packed into each output example. By default, there's no upper bound, but you should also remember that the larger the number of neighbors in each NSL training example, the longer it will take to train your model. When a value is specified for this parameter, the top neighbors by edge weight are used. Finally, there's the ID feature name parameter, which identifies the name of the feature in your input examples that contains each example's unique identifier. This is just like in the graph builder. It identifies the node ID for matching it up with the edges in the graph. Okay, one last thing, which is that both the graph builder and the pack neighbors tools can be run as standalone binaries using the commands shown here. The available flags for each program have names identical to the parameters I described on earlier slides. And that does it for the NSL data preprocessing tools. Cesar is going to talk next about how to train an NSL model on a natural graph. But I guess first I should ask if there are questions.
There are some questions on the chat, which I can summarize for you.
Okay.
First question is from Andrew. What if your original input data is not in the form of embeddings, but for example, tabular features? Is there a way to learn the embeddings jointly with the NSL learning process, or do you need a completely separate pre-processing step to map them into static embeddings?
Yeah, unfortunately, we don't have any NSL support for that step. You will need to generate your own embeddings for your input instances, using some sort of like autoencoder or some other technology.
Thanks. Next question from Chun-Sung. It seems that the ontology structure of a similarity graph is not necessarily predetermined. The edges or links between nodes can be established purely based on the similarity of embedding vectors. Not sure if there's a question or a comment. But so maybe I can try and add some context to that. So the graph building API in NSL does require the inputs to contain embeddings, but a similarity graph can certainly be built without using embeddings. Like if you have a natural relationship, like Allan mentioned earlier in his talk, that captures similarity. So then you can represent that graph in a top separated value format that NSL can then consider.
Yes.
Next question from Arthur. Does the LSH splits perform better than an approach based on KD trees to find neighbors?
I'm not sure I fully understand the question because well, I should just say we haven't done any kind of investigation or experimentation to see if KD trees would be an alternative approach that would work.
Okay. Next question from Chun-Liang again. I'm wondering if cosine similarity can capture a higher degree of similarity structure in the graph. The similarity of neighbor nodes can be defined by first degree or second degree or higher degree of similarity. I'm not sure
I understand that question. I mean, maybe if by first degree and second degree you're referring to the number of hops but away from the labeled node in the graph, we really only care about immediate neighbors when we do the graph-based regularization during training.
Cool. Question from Ahmed. Given a fully labeled training dataset, do you expect the structured learning where the similarities are not organic, that is fully implied from the training set itself, to improve the accuracy?
Yes, so even if all your examples are labeled, we can still benefit from the neighbors when we're doing the graph-based regularization during training. The structure obviously can come from multiple sources. The similarity graph can be inferred by features of the examples, as we've discussed, using the embeddings, but they can also be, they can come from other sources that may be not even really represented either directly or indirectly in the instance features or embeddings. So I do believe you can definitely get benefits from using graph-based regularization even if all your training examples are labeled.
I think there's another qualification in the question where I think they're asking if all of the similarities are fully implied from the training set. So they don't have an orthogonal source of similarity. Like, do we still expect the model to do better by doing the structured learning?
Well, as Da-Cheng mentioned, there are two sources, there are two benefits from NSL. One is improved accuracy and the other is model robustness. I think it will depend on a case-by-case basis, but there may very well be a case where you may not see much improvement in accuracy, but you may see an improvement in model robustness.
Thanks. So another question from Arash. Is there support for property graphs?
No, I don't know what that means, so I will say no, unfortunately.
But I mean, I guess at a high level, if the graph ultimately captures some sense of similarity between pairs of nodes, then you could still represent it as a graph that NSL can consume for doing graph-based regularization, if that makes sense.
Yes.
Question from Ayush. Can we incorporate NSL with TF ranking?
I don't know. Can anyone on the team comment on that one? I don't have an answer for that question. Sorry.
So basically, in NSL, we provide both the TensorFlow operations, TensorFlow libraries, and also the sort of like a package solution, right? Like the estimator or a Keras models. So like both, I think, could be used together with the TF ranking. Let's say in a TF ranking method, they could include our operations. Or, for example, if they also support estimator and Keras model, then two frameworks or two modules could be used together.
Okay, I think Arash just explain what property graph is. Property graph is very similar to knowledge graphs. Each edge is capturing a different property, example, parent-child versus friend-friend relationship. So I think basically they have like some heterogeneous graph structure that still captures similarity. So I think graph regularization is still very applicable for those graphs as well.
Yes, I agree.
Yeah, and adding one more detail, we have also done some like research work on learning these like graph embeddings based on knowledge graph or the property graph, like Arash mentioned. So if anyone, for example, if they are interested in this aspect, all of the tools and libraries and the research work has also been open sourced in the neurostructure learning GitHub. So feel free to look them up.
Another question from Tisha: can we visualize NSL models using TensorBoard?
That's a good question. If, let's say, the visualization is about the TensorFlow computational graph, then yes. But if it's about, let's say, the data graph, let's say similarity graph or the relation or property graph, then currently TensorBoard hasn't supported this functionality. So that's a really good question.
Okay, I think maybe in the interest of time, we should move on to the next presentation.
Okay.
Thanks, everyone.
Thanks, Allan. And thanks, Da-Cheng, before. All right. Hi, everyone. You are now familiar with neurostructure learning and how NSL can be useful. So let's dive into one of its use cases, graph regularization with natural graphs. To start, what is a natural graph? As Allan has mentioned, a natural graph is a collection of nodes which are inherently related or connected, given the properties of the dataset. The edges can be of different forms. For instance, if we have images that co-occur on different websites, we could use that to build a co-occurrence graph. Or if we have a collection of scientific papers, we could use how each paper cite each other as edges to build a citation graph. One example we'll discuss in detail today with a hands-on collab is a dataset about Twitter. As it's the case with many online conversation threads, a reply thread on Twitter contains tweets which are naturally connected by the reply structure. So as you can see here, typically you'd have someone starting a conversation and then you can have a potentially nested structure with multiple replies. And as you also know, sometimes we might see text in social media online that is accurately representing what's going on, whereas in other cases, we might be seeing some representations which don't match what is happening in reality. So the dataset at hand is the Pham dataset, which contains a collection of Twitter rumors for several news events. And source tweets are annotated by professional journalists according to their veracity. So basically, whether or not what is being said on the Twitter rumor is true or false. So let's take a look into the collab. All right, graph regularization for Twitter rumor veracity classification using natural graphs. As mentioned, this tutorial is going to use the Pham dataset, which is the Twitter rumor veracity classification, a binary classification task. So each annotated source tweet is either true or false according to the professional journalists. And the tweet texts are going to be used as input for initially computing the embeddings. As Allan mentioned, we need those as features for the model. And for that, we can use several pre-trained NLP models. For instance, we can use Bert, Roberta, Albert, to name a few. And those representations are then used as features either for a baseline multi-layer perceptron classification model or for a similar version with the graph regularization added to it, in which we define the structure of the tweets just based on the structure already present from these conversations. So to start, we need to install some dependencies and then import them as usual. So here we are using the NSL neurostructure learning library, as well as Hugging Face transformers and tokenizers, which are going to be used to compute the embeddings for source tweets and their replies as well. Here we import the dependencies, and we also check the TensorFlow version and whether or not GPUs are available. This can be useful for, let's say, running the inferences on batch mode and speed things up. The data set as described contains Twitter rumors, and they are associated with diverse news events. And each source tweet is followed by all the reactions, so basically the replies within the conversation thread. And this reply structure defines the natural graph that we are going to use for NSL. And we also have veracity labels that were added as annotations by professional journalists. And those are associated with each source tweet. So they're not annotating each individual tweet on the conversation, but just the tweet that started the conversation. So here's the attribution of the data set, and thanks to the authors, Elena, Maria, and ArcSight, who have given us explicit permission to use this, and it's licensed under the Creative Commons library, so this should be fairly simple for any of you to use it as well. So here I will skip downloading and extracting the data set because it was already pre-computed a while ago. And as you can see, so there are several different news events. For example, Germanwings crash. And each of these news events has several Twitter rumors associated with them. And each source tweet has also a bunch of replies within the conversation thread. So just checking that we have here all the different news events for which we have these annotations. So we have roughly 10 of those different news events. And let's now define a handful of helper functions that will help us to start from the raw data and put it into the right format that we are going to use for either graph regularization or just for computing the embeddings or putting them in the right format. Yes? Did someone say something? Okay, so this first function is provided with the data set, so it's just copied pasted here as it was for transparency. So it basically converts the labels, the annotations from the professional journalist on whether or not each of the tweets, the source tweets, is true or false. So these are the veracity annotations. And as you can see, they're basically three classes because not all of the tweets were verified. So it will also filter out the ones that do not have these labels. But other than that, it's a binary classification task. Each source tweet, the verified ones, is either true or false. Here, it's a helper function that will load the raw data set from the directory that we just downloaded and extracted to. So these are just JSON files, and we'll go through the structure. And basically what we want from here is to get the annotation, the professional journalist label, also the structure. So given each source tweet, what are the reactions to it? We want, of course, the source tweets, the ones that started the conversation, and their corresponding reactions. So we'll collect all of that from the JSON files. And after that, the next function here is to starting from the verified rumor tweets. So what we do here is that we will extract a list of dictionaries, and this will be in a more convenient format for us to use later, in which we have associated with each entry, we have the label. So this is the annotation, as well as the source text, so just a string, the tweet, and a list of strings for the text tweet of each reply associated with the source tweet. And here we're verifying that we have the topics within the folder that we extracted the data set into. Next, we have the configuration from Hugging Face for us to use the transformer package. So here, as you can see, there are several examples. This is by no means an exhaustive list. There are many more pre-trained NLP models that can be used for computing these representations that we can use for downstream tasks. And this is just a few examples that you could just uncomment and use one of them. We have different sizes of BERT, ExoNet, Roberta, Albert, T5, and Electra. And as I said, there are many more that are not listed here. And the reason for having them commented here is because not only it takes time to download, but also you could easily run out of memory if you try to download many of these large models. And just to be clear, this is very common practice in NLP to leverage those pre-trained language models, because you can pre-train them on much larger data sets and then leverage that for downstream tasks in which the number of labels is much more limited. And the most common way of doing that is to fine-tune the model all the way, meaning that as you have some label data, you can backpropagate and adjust all the weights of your entire backbone network, not just the final classification layer. But here for this tutorial, for the sake of simplicity, we are just using the embeddings, the fixed embeddings as features for the multi-layer perceptron that we are going to train. So this is also known as the feature vector approach, or using the pre-trained model as a frozen network. And here we have some of the functions that allows us to tokenize and perform model inference for some of the Hugging Face models that we saw before. And again, this is just a few examples. We have here BERT and Albert and T5, and there are some more listed before and many more available on the website. So for an extensive list, please check the Transformer library documentation on the website. Here are just a few examples. And for this tutorial, we're going to be using Albert Base, which is not too large model and allows for a pretty good value for cost in terms of model quality. So for some of them, we define two different ways for performing the inference. So either we perform one inference at a time, or we can also run inferences in batch mode. And batch mode is particularly helpful if we have GPUs or TPUs available, because we can run them in parallel, and that can speed up a lot the inference time. And another thing that is required for the batch mode is that we need to have a fixed max sequence length. So that means either we truncate examples that are too long, or we pad examples that are too short. And we define here a constant max sequence length, which for Twitter doesn't have to be too long, because most tweets are short. There's even a character limit on how long the tweets can be. And here we define just a dictionary for convenience, mapping some of the names of how to compute the inference for some of these models. And we are going to be using here Albert Base, just a single inference at a time. So here's an example. Let's take the pre-trained model from Albert Base with the corresponding tokenizer, and let's compute the embeddings for this toy example phrase, why is the sky blue? So here, as you can see, we get this tensor, which has 768 floats. And this is pretty typical for these models. So 768 is the hidden dimensionality for Albert Base, but also for BERT Base. And even GPT-3 Base has the same hidden dimensionality of 768. So there are several ones depending on the size of GPT-3. The largest one has up to 16 times that hidden dimensionality, and the model is way larger. So just for reference, BERT Base, we're talking about it's 108 million parameters in total, whereas Albert Base is lighter. It's only 12 million parameters. And for GPT-3, we go all the way to 175 billion parameters. So that's over 1,000 times larger than BERT Base. And yeah, the models keep growing with time. So here we define the set of hyperparameters that we are going to be using for training the NLP classifier and also for the NSL graph regularization. So just a few comments about them. So the number of classes, this is true because we have a binary classification task, and this basically defines like what will be the final perceptron layer to which we're going to apply the softmax in the end. The embedding dimensionality, this is the 768, which is given by the pre-trained model we chose, the encoder that we chose. Now the NSL parameters, so here we have for neural graph learning, we're going to be using a multiplier of 0.1. The distance type, we're going to be using the L2 metric, and the max number of neighbors, we're limiting this to 5. So for each tweet, we can include up to 5 replies from the thread. And this is the architecture of our perceptron. So we have a fully connected, we have 2 layers of fully connected, and each of them has 64 neurons. We're going to train this for 50 epochs with a batch size of 128. And if we were running the inference of the embeddings in batch mode, we would be using 32. And we also add a dropout to our perceptron to mitigate overfitting. And a couple more helper functions before we get into action. So this helper function is gonna add the embeddings to the data format that we already computed. So we had each entry was a dictionary with a label, source text, the tweet, and the reactions. And we would add in batch mode the embeddings for the tweets, the source tweets, as well as their reactions up to the max number of neighbors that we are going to use. So the way this happens is that first we have to generate the batches depending on the batch size that we defined of 32, and then we compute inferences for each batch, and we add that to the data that we have. An alternative way, which is pretty equivalent, except that instead of first batching and then running the inferences in batch mode, we can run the inferences one at a time, and this is what we're doing here, just for simplicity and for not using GPUs or TPUs for better parallelization. So here we're taking the same input, and the output is also the same. It's just that there's no extra middle step of computing the batches and adding them back. All right, so here, this method just loads the data set for the input topics. So the topics, those were the news events that we had. So as you can see, we had a total of about 2,400 different rumor tweet threads, from which we're going to use 1,700 because not all of them were verified. So we're not using the verified ones. And here, let's take a look at the random sample. So this random sample, things look good. So the label, this means that this is true. And here we have the reactions. So all the tweets that reply to the source text, this was the tweet that created the conversation, basically. And then we have a few others. So we have some tweets that were classified as misinformation by the journalists, and we have the associated reactions, and again, the source text and so on. So this is just a random sample from the data set. The next step is pretty slow. So this was pre-computed, and when not running in batch mode, this takes a while, so I'll not run it again. We compute the embeddings for each item, so the source tweets and the neighbors from the thread, and we add that to the data that we're going to be using. So I'll skip this step, and the next one is, given the data set, we find a way to split it into train and test. So again, there are multiple ways to do this. For instance, we could be, since we have the news events, we have the topics, we could be splitting in a way that there's no topic overlap between train and eval set. We could also be splitting by timestamp in order to avoid event overlap in a different way. So here, just for the sake of simplicity, the simplest way we could do this is probably to just shuffle the data set and do like an 80-20 split. And we also define the constants that we are going to be using for the signature of our TF examples that we are going to be using for graph regularization. This next helper function it converts from the previous dictionary we had into a tuple, and this tuple contains the node tensor and the neighbor tensor. So it's just reshaping them in a format that we are going to be using for our model. And here, let's take a look into one of the examples from the train and test tensor. So the train tensors, if you look at the first example, we have here the embeddings. So this is again the array that has the same dimensionality as before. 768 is of the same type, and we have the label as well. And likewise for the test also has the same format. Here we finally create a train and test data set in the format that is going to be used as input for the NSL library. So as Allan described, we're going to be consuming a TF record data set and containing the TF examples that were produced from our features and labels. And here another important point is that we only add the neighbors for the training set. So these are used during training, but not during inference time. So this is the regularization aspect that Allan has talked about. All right, so here we can run this again. It just reshapes, puts the data into the right format, creating this TF data and with the TensorFlow examples. And now we can take a look into the train and test data set in the right format. So here we have the embeddings. For the train data set, we also have the NSL feature. So we have the embeddings and the weights. So we are using here fixed weights. Again, for the sake of simplicity, we could be using different ways to produce that. For example, depending on how we select the neighbors from the thread, we could be, if we take only direct replies of a tweet instead of the nested ones, or we could also use some similarity function to compute the weights. Maybe we wanted to diversify the tweets or only take the ones that are aligned with the source tweet. We could do different things here to change the weights for each neighbor. So here, this example, we have the embedding, and then we have the embeddings of the neighbors as well, and the weights of the neighbors. And so here we can see this TF tensor. So it's a batch because now we have the batch size that we're going to use for the model 128 and 768. This is the hidden dimensionality that comes from Albert Bayes. The next one, we have the batch of neighbor inputs, and again the same. So each neighbor inputs will have the same 128, 768 dimensionality. Here we have the weights, so we have a total 128. And then we have the labels as well. So it's a bunch of zeros and ones because this is a binary classification task. These are the veracity labels. And the test data set looks similar. The difference is that, so we don't have the neighbors are not included in here. So as you can see, we have the embeddings with the same dimensionality matching the training set. And we also have the labels that we're going to be using for evaluation, but we don't, the features that we use from the graph are not included in here. And to create the MLP model, we define it in different ways. So just for you to have different options. So one way is to use the Keras sequential, in which we start a model as Keras sequential, and then we add the two fully connected layers after the input layer, and then at the end we add the final dense layer, which has the number of classes and the softmax activation. An alternative way is to use a functional API, which basically means we can start the model by defining what are the inputs and outputs, and then we invoke the TF Keras model that converts from the inputs into the outputs. So here the inputs is again pretty similar. We start from our features, and then we add the dense layer, the two fully connected layers, each of them with the ReLU activation, and then in the end we have the classification layer, and we are adding manually here the dropout layer because this is only invoked during the training. We are going to be using this by default. And the other way to do this is to inherit from the TF Keras model class. So basically we create a class, let's call it NLP, and then we have to override the methods that are relevant. So for init, we define the layers as, again, the two dense layers with 64 units each, and also the rel activation. We also add the dropout, and we have the output layer, the classification layer with two nodes and a softmax activation. And then for the call, we just apply them, converting from the input embeddings all the way to the output layer.
Hey,
So
Cesar, I see.
yeah,
Before you proceed, I think there's a question on chat which I think will help if you address.
sure.
In this person, Chun Liang, he says he's kind of lost in this notebook. It seems to me that it's a regular pre-trained Albert model for text classification in which code snippets the graph structure is introduced. Second question is, for every source tweet sentence, what are the neighbors? And the third question is, where can I find the regularization part in the loss function?
Right. So for the first question, so where we define so the pre-trained models, correct, we are using Albert as just as one example. We have multiple possibilities. Let me get back to that. So this is where we define the models, and the way we compute the neighbors is that they are being given by the data set. So if you go back to the data set, we have for each, so basically we have the data is formatted in a way that we have the source tweets, and we also have the reactions, and we also have the structured JSON file that tells us for each source tweet what are the associated neighbors that are replying to it. So we have all that information from the data set, and this is, again, true as a reminder, this is a natural graph. So we are not computing the graph based on any similarity of the embeddings. We're just using the reply structure from the graph. And the other question is, where do we use this graph? So we're going to get into that. We're going to first train a normal baseline vanilla MLP without the graph regularization. And then we're also going to train a similar model with the graph regularization that uses the structure that we got from the data set. So there were 3 questions. Let me check if I answered all of them. So the first one, where is the graph structure introduced? Yeah, so we get that from the natural graph, from the structure, and we're going to use that on the last step. I can show again the exact piece of code in which we take the neighbors and also add the specific NSL signature that we're going to use. And for every source tweet sentence, what are its neighbor nodes? Yeah, those are the replies coming from the data set. So we don't compute that, we just read the data and parse it in the right way. Where can I find the regularization part in the loss function? So this is built in the NSL library. We're going to see that in order to change from the baseline MLP to use also the graph regularization. So by using the library, we can just specify some parameters and use that. It will take care of the regularization part for us. Okay, so
Cesar, can you point to the code snippet where the packing of
Yeah.
neighbors is happening?
So the one that adds the NSL signature, right? Yeah. So here, so this method make data set that takes as input the list of node tensors and the neighbor tensors. So, and this will produce the TF examples in the TF record data set that we need for the NSL library. So what we do is that only for training, so we don't add those for the test set, for the eval set. This is only for the training. What we do is that, so we're going to iterate up to the number of neighbors, and we are going to add. So basically, here there's a trick. Like we will always add the full number of neighbors, but if there are fewer than the limit, which is 5 in this case, we are just filling that with 0, but we specify that the weight here is 0. So this is not going to be taken into account. So what we do is that since we pre-computed the embeddings, we can add to this feature key, we can add the embeddings that were already pre-computed. And the weights that I mentioned, for simplicity here, we are using fixed weights of 1 for each neighbor, but there are multiple ways that we could come up with to use specific weights depending on, for example, the distance to the thread or how nested the comment is, or maybe some similarity or opposing viewpoints. So we could also try some different things in here. Yeah, so, and we'll get into where this is plugged into the NSL library. So here we define the models. So let's take a look into the base MLP. So this is the multi-layer perceptron, and we're using here the functional API as an example, but we could be using the sequential or the subclass as well. So here what we have is that the input layer, the embeddings, we have a dimensionality of 768 as expected. So this is because it's coming from our base. If you're using per base, it would be the same, for instance. And then we have two fully connected layers with 64 neurons each, and each of them has dropout. So the number of parameters initially is 64 times 768 plus the 64 biases. And then we have 64 times 64 plus 64 biases. And then finally, we have the classification layer. We have two, again, a fully connected dense layer. We have two, so 2 times 64 plus 2 biases. We have 130. So in total, we have to train roughly 50K parameters. So here we compile our model. We use the Atom optimizer, which is pretty standard. And we use as a loss function the sparse categorical cross entropy, and we keep track of the accuracy metric. And then we train that for 50 epochs as specified on the hyperparameters. So here, as you can see, the accuracy goes up quite a lot. So this is a suggestion that this model is probably overfitting despite the dropout. And now we define a function that will evaluate the model this time on the test set, because we have the labels there as well. So once we compute here, we're getting an accuracy of 0.64. And just one comment, this changes, there's quite some fluctuation if you do different runs, even without reshuffling the data set. There can be quite some variance in here. So ideally, if you want to do any more rigorous benchmark, you should run this several times, take some average, or probably even better, have a more robust approach, like fine-tune your model all the way instead of this MLP on top of the our pre-trained model. So now what we do here is that we create a model in a very similar fashion to what we did before. So again, we're using the functional API with the same hyperparameters. And now the difference is that we invoke the NSL library to specify the config that we want to use for graph regularization. So here what we do, we are using the number of neighbors up to 5. We have the graph regularization multiplier, which was defined also in the hyperparameters of 0.1, and we're using L2 as the distance type. And then here we create a model from the NSL library that takes as input the base regularized model and the graph regularization config. And then we compile the model with the same config that we had before. Again, Atom optimizer, sparse categorical cross entropy loss, and we keep track of accuracy. And once more, we run this for the same number of epochs. So one difference here is that you see that we have not only the accuracy, but we also have the scaled graph loss as well that changes as the model iterates. So in the end, we get here final accuracy, and we can also evaluate the model with the graph regularization. So I hope this is clear as a basic example of how we can plug in using a real example data set, how we can plug it in the NSL library. And the library is quite straightforward to use because all the sophisticated parts are done under the hood. So the built-in methods are pretty helpful. And yeah, so thanks everyone for your time. We can answer some questions, and after that, we'll have a 10 minutes break. So one question, what if we combine source tweet text with all reply text and consider the whole as one document instead of treating them as graph structure? Right. This is perfectly valid as an approach. So there could be some limitations. So one is that traditional transformer-based models, the complexity has a quadratic term on the max sequence length. So I know there has been quite a lot of recent work over the last year towards linear complexity and attention for transformer-based models. But the ones we have seen so far, this quadratic term makes it pretty difficult to scale beyond a certain limit. So in practice, like with default transformer models, it's normal to see things with up to sequence length of 1,000 tokens. But going beyond that is it's usually pretty tricky to just to make things fit in memory on a normal TPU. And there are recent work like things such as Reformer that using things like locality-sensitive hashing that Allan mentioned allows you to process sequence with up to 1 million tokens all at once. So this is definitely a possibility. That would obviously defeat the goal of this tutorial, since the whole point was to show an example of how to use NSL. But your question is valid. It is a possibility to, depending on how many you can include. And to be fair, even with 1,000 tokens, if we're talking about tweets, that's already plenty of tweets. So we could include, well, of course, if the thread goes viral and there are way too many of them, we'd have to either truncate or find some way to combine, to split and combine the different representations. But it's one possibility to try. Then we apply pre-trained language models to capture their semantic dependency in this document classification problem. Okay, so this is the continuation of the same question. Yeah, as I said, this is valid. And if graph representation beats this document classification, so I haven't experimented with that. So as I said, like lots of things that were in this tutorial were, for the sake of simplicity, they were as simple as possible. Like even when defining the train and test split, we were just doing a very simple split. I was doing also the simplest way to select the neighbors, just taking the first that appeared in the file structure. And also, we are not fine-tuning the models all the way through for our task at hand, but just taking the frozen backbone or the feature vectors. So if you want to improve this task as like a benchmark, then it's worth trying many things, including your suggestion. XLNet or long former to handle long document classification. Yeah, as I mentioned, there are quite some recent work. I mentioned Reformer. Long former is another one. There's also Lin former. There are many ones there. You can also do attention pooling. There are ways to do like sparse attention. You can do quantization. There are many techniques. It's the goal. There are other tutorials that are specifically about how to handle long document classification. XLNet would not have been much of an improvement. It is one possibility that was also one of the models show that on the list from Hugging Face, but it doesn't have the linear complexity and attention as some alternatives have. Yeah, just to be clear, the L, so XLNet stands for transformer, extra long transformer, because the transformer architecture is longer than the typical one. Did you consider a way to evaluate the quality similarity graph? That is, some adjacencies may actually make the network worse if the examples aren't actually really close. But for lack of examples, they are the most near neighbors. Yes, this is a perfectly valid comment. So I mentioned when selecting the neighbors that there are many ways to explore it, including you could do some semantic analysis. For example, just take the ones that are semantically similar. You could even use textual entailment models to take the ones that are supporting the source tweet as neighbors. So your question is totally valid. You could have like someone pasting, let's say the moon is made out of cheese, and then the next reply is, no, that's totally wrong. The moon is not made out of cheese, right? And then those will probably have very different, hopefully have very different embedding representations, and this would actually quite likely make the approach not work as well as it could if we were just selecting the neighbors that were supporting the initial one. Yes.
In the interest of time, maybe we can have a short break. We'll be sticking around to take more questions, but we'll resume the next session in exactly 10 minutes.
All right.
So yeah, I mean, everyone, I mean, feel free to take a short break. We'll be here if you want to stay and ask questions, but the next session will start in 10 minutes. Yeah, before we start the next session, I mean, we still have about 5 minutes. So if anyone has any questions, for any of the earlier presenters or about neurostructured learning in general, feel free to ask them. We'll start in a minute. Okay, let's get started. I hope everyone can see my screen.
Yes.
Thanks. Okay. So hi everyone. My name is Arjun Gopalan, and I'm going to be talking to you about how to do graph regularization with synthesized graphs in this session. So in the previous session, you looked at how to do graph regularization with natural graphs. And to recall, a natural graph or an organic graph is a graph that's formed by some inherent relationship that exists between data points. And so you looked at a specific example in classifying the veracity of tweets, where the natural graph was formed by the reply structure in the dataset. And so in this session, we'll look at how to do graph regularization when we don't have a natural graph to begin with. So while natural graphs are extremely common, there are many machine learning applications where we won't have a natural graph to begin with. So imagine you're doing simple machine learning tasks like text classification or image classification, then we don't necessarily have a natural graph to begin with. So how can we apply graph-based regularization to handle such machine learning tasks? So the title of this presentation might have given this away, but the idea is to build or synthesize a graph based on your input data. So graphs can be built in many different ways, but in this presentation, we'll be looking at the notion of using embeddings to build a similarity graph. And so this process involves taking raw instances in your data set, and these can be of any modality, be it text, audio, images, or even video. And then you convert them into corresponding embeddings. So converting them to embeddings can be done using some pre-trained model, such as a model on TensorFlow Hub. And you just looked at how to use an Albert-based model in the previous tutorial. So once you convert instances in your dataset to corresponding embeddings, then we can compute a similarity score between pairs of embeddings. And so here, you can think of using a similarity score such as the cosine similarity to compare how similar pairs of embeddings are. And so for every similar pair of embeddings, we add a corresponding edge in the resulting graph. And so if you repeat this process across all instances in your dataset, you end up with a similarity graph where edges in this similarity graph correspond to the similarity score that were computed between pairs of embeddings. So let's illustrate this workflow for a specific example. So we'll be looking at the task of sentiment classification for the IMDb dataset. So the input examples in this dataset contain text-based movie reviews, and the task is to classify them as good or bad. So you're essentially trying to classify the sentiment of the movie review. And so the graph regularization workflow for this example looks like the following. So we start off with text-based movie reviews. The first step is to then convert the text-based movie reviews into corresponding embeddings. And to do this, we use a pre-trained embedding model on TensorFlow Hub. Once we end up with dense embeddings for each text-based movie review, then we use a graph builder from the neural structure learning framework. And this allows you to build a similarity graph based on these embeddings. So once you have a similarity graph, neural structure learning also provides an API to do training data augmentation, like you looked at earlier. And so this process combines not just the features of the original text-based movie reviews, but also includes the features of their corresponding neighbors from the similarity graph that we just built. And finally, these augmented training examples are passed to the downstream model trainer, which incorporates the graph regularization loss term. So this is the high-level workflow of the model that we're going to look at shortly. And so I've linked to a Colab notebook here in this slide. So I'm going to go ahead and click it so we can start working through it. Feel free to follow along in case you want to, but this tutorial is also published on our website should you choose to revisit it later. So I'm going to connect to a host at runtime here. And so again, in this tutorial, we're going to be looking at how to do graph regularization for sentiment classification on the IMDb dataset. And so here we don't have a natural graph to begin with. So we'll look at how to build a graph and then use that graph to do graph regularization. And so the high-level workflow, just to recall, is you take the movie reviews, text-based movie reviews, convert them into embeddings using a pre-trained embedding model. So here, you're free to use any embedding model of your choice, like Word2Vec, Swivel, or even more complicated models like BERT. And once you convert them to dense embeddings, we build a similarity graph using the graph builder from neural structure learning. And then we use the graph and the features in our data set, in this case, again, text-based movie reviews, to create an augmented training data set. And the augmented training data set includes the features of the original reviews and the features of their corresponding neighbors. And finally, we can use this augmented training data set to build a Keras model. And again, in this tutorial, we're going to be using Keras for illustration, but neural structure learning also supports the use of estimators for model building. And so the only requirements here for this tutorial are two packages. One is, of course, the neural structure learning package, and the other one is TensorFlow Hub, because we're going to be using a pre-trained model on TensorFlow Hub to convert text to embeddings. And as before, we'll import all of the dependencies that we need. So here we are running TensorFlow version 2.3.0, and then we're also enabling eager execution. It helps with an interactive experience on Google Colab. And so now about the dataset itself. So the IMDb dataset contains 50,000 text-based movie reviews from the Internet Movie Database. And these are split into two equal parts, 25,000 for train and 25,000 for test. And so in this tutorial, we'll be using a pre-processed version of this dataset that's part of the Keras framework in TensorFlow. And this pre-processed version contains integer-based word vectors for each of the text-based movie reviews. And so let's take a peek into one such example. So here, as you see, the training example, the first example here is just an integer-based word vector. And one thing to note that is all examples in the dataset can be of different lengths. And so you want your model to be able to handle variable length text input. So as you can see here, the first example has about 220 words and the second one has about 190 words. So although the pre-processed version of this dataset contains integer-based word vectors, it still is useful to be able to convert from the integer-based word vector representation back to the original text-based representation. And there are two reasons for why this can be useful. So one is in order to reason about the quality of the final graph regularized model, as well as just look at how the similarity graph ends up, it's useful to be able to look at the actual text-based representation for the reviews. So you want to be able to see whether two reviews that are semantically similar, whether they share an edge or not in the graph. And if you just have the integer-based word vectors, it's hard for us to reason about that. And another aspect is that because we're using a pre-trained embedding model in this example, the input requirement is that the reviews be in the text form. So we want to be able to convert from the integer-based word vector to the text-based movie reviews. So here we're just building a reverse word index to map each word ID to its corresponding word from the dictionary. And so here we just try to decode the first movie review, and as you can see, we have a paragraph that summarizes this person's review of a specific movie. And so now the first step is to actually build a graph, because we don't have a natural graph in this example. And so in this example, we're going to be using a simple pre-trained embedding model, the swivel embedding model that's just that just has 20 dimensions. And so we define that as a Keras layer in our model, and then we go ahead and convert the examples in our dataset, text-based examples, to corresponding embeddings. So we have this helper function called create embeddings. So it takes the integer word vectors from the training dataset and then converts them into embeddings and persists them into this TensorFlow record file that contains embeddings. And so each embedding example basically contains two features. One is a unique identifier for that example, and the other one is the floating point embedding vector, in this case, a 20-dimensional embedding vector for that example. And so I think Allan mentioned this earlier in his presentation. This unique ID feature is essential to associate every example in our dataset to its corresponding representation in the graph. And this is important because that's what allows us to create the augmented training dataset. So now that we've created embeddings, let's go ahead and build a graph using these embeddings. So neural structure learning provides a graph building API to build a similarity graph. And so here, again, we're using locality-sensitive hashing to speed up the graph building process. Because again, here, because we have 25,000 training examples, if you were to do a naive all pairs comparison for graph building, then you will end up doing 25,000 choose two comparisons, which can be quite expensive. So instead, we use locality-sensitive hashing, which dramatically speeds up the graph building process. And so here you see that there are three parameters here that are important for the graph builder configuration. So one is the similarity threshold, and this allows you to specify the edge weight threshold below which you want edges to be dropped from the output graph. And so you can control this in any way you want. But one thing to keep in mind is that if you set the similarity threshold very low, then you might end up with low quality or noisy edges, which may affect the model negatively. And so then we have the LSH splits argument, which is 32. And what this means is that we're essentially splitting the input embedding space 32 times, and each split basically potentially doubles the number of buckets that we end up creating. And so in the extreme case, we can end up with a maximum of 2 to the 32 buckets. And because, like Allan mentioned, when we're doing this bucketing process and we're only computing edges within each bucket, it's possible that points that are otherwise similar to each other may end up on different buckets. And we don't want to end up missing out on these good quality edges. So we repeat the LSH bucketing process a few times. And that's controlled by this LSH rounds argument. In this case, we repeat this 15 times. So you can certainly reduce the number of rounds here. So here we just chose 15 because this gives us the maximum recall for the number of edges compared to the all pairs comparison. And so now we have the graph built. As you can see, the output is a tab separated value format, and each line corresponds to a directed edge in this graph. And so here we have about 860,000 directed edges, and this includes a reverse edge for every edge. So if you just count the bidirectional edges, then you have about half the number of edges. So it's important to note that the quality of the graph and by extension, the quality of embeddings are very important for graph regularization, because that's what the model uses to penalize itself from when it makes a misprediction on nodes that are connected by an edge in the similarity graph. So you want to make sure that your embeddings and the graph that you have captures similarity quite well. Okay, so now that we have a graph, the next step is to actually define the features for our model. So here we have 3 features in every example. So we have the ID feature, which is the unique identifier for a given example. Then we have the integer-based word vector that captures the movie review for that example. And of course, the ground truth label for that example. And so here we've just created TensorFlow records for all of our examples. So we have included both train and test in our data set for now. So now that we've defined the features of our model, the next step is to augment our training data set to include not just the features of original reviews, but also the features from neighbors in the graph that we just built using embeddings. So neural structured learning has this API called pack neighbors that again Allan described earlier. And this basically takes as input the first argument, which is the labeled examples that are used for training. The second argument, which is empty here, is a set of unlabeled examples. So if you have a separate set of unlabeled examples, NSL can still use those unlabeled examples in the training process. So in this case, we have a fully labeled data set, so we omit this argument. And the third argument is the similarity graph that we just built. And the output of this process is an augmented training data set, again persisted in the TF record format. And so here we have 2 arguments specified in this API. We want to make the graph symmetric, so we set this add undirected edges to true. So which means that when we're doing the regularization, we will be including both copies of an edge, both directions of a given edge. And we'll be using up to 3 neighbors when we're augmenting the training data set. So that's done. So now let's look at some hyperparameters that we're going to be using in this example. And so here, again, this is a binary classification problem because we're trying to just classify the sentiment of a movie review as positive or negative. And we define this maximum sequence length variable, and this allows us to use a fixed length representation for every movie review. As we saw earlier, movie reviews can be of variable length, but ultimately the model needs a fixed length representation for every input. So we use 256 as the maximum sequence length. So for reviews that are longer than that, we truncate them down to 256 words. And for shorter reviews, we just pad them up to a maximum of 256. And the vocabulary size that we use for this example is 10,000. What this means is that we're just going to be using the 10,000 most frequently occurring words from the dictionary. And then some graph regularization hyperparameters. So again, we're using L2 as the distance function when we're comparing the distance between neighbors. We're going to be using the graph regularization multiplier as 0.1. So this controls the relative importance of the graph regularization loss term with respect to the total loss term that we have. And so this means that 10% of the contribution is from the graph loss. And we'll be using 2 neighbors for doing the regularization. So notice that the number of neighbors you use for regularization can be at most the number of neighbors you used when you created the augmented training data set. So if you recall, we used up to 3 neighbors here when we created the augmented data set. So we can specify a value anywhere from 0 to 3 when we're doing the actual regularization. And then there are some model architecture parameters. So the dimensionality of the embedding layer, the dimensionality of the LSTM layer if you were to build an LSTM based model, and also the dimensionality of a fully connected layer. So let's go ahead and actually train the model for 20 epochs just so we get some stability. And so now we've prepared the augmented training data set, and we're ready to go ahead and train our model. And so here we convert our train and test. I think I missed executing a cell. So here we convert our train and test examples into tf.data.dataset objects. So that's what these 2 lines end up doing. So we have this make dataset helper function that creates this for us. And so in this line, you see when we're defining the training dataset, the input is actually the augmented training examples that we created earlier. And we take these examples and create a dataset object out of it. And let's quickly look at what this function looks like. And so for every example that we get, we parse the features from the corresponding movie review, in this case, the variable length integer word vector, and also the corresponding ground truth label associated with it. So this is similar to how you would define an input layer for any machine learning model in TensorFlow. And once we do that, we also want to parse the corresponding neighbor features that we augmented earlier. And again, graph regularization only works in training, so there's no change in the serving workflow. So if you're in the training mode, then we additionally also parse the neighbor features that we created based on the similarity graph. And so in this case, we take the word vector for each of our neighbors from the graph as well, and use that as an input additionally to the model. And so here, for each of these neighbors, we also use the corresponding edge weight. The edge weight is the cosine similarity score that was computed between their corresponding embeddings. And in case a particular example does not have the maximum number of neighbors, then we just use a weight of 0.0 for those examples, because then they won't contribute to the regularization term. And so once we define our trained data set, then we also define our test data set. And again, as I mentioned, the test data set will not include the neighbor features, because we don't use neighbors during evaluation or serving. So now that we have our data sets, let's go ahead and train the model. In the interest of time, I'm actually going to go ahead and skip training the base model. We'll directly train the graph regularized model. And so here we have 2 examples here for the model architecture. So one is a feed-forward neural network. And so here, this is a simple 2-layer model. So first we have the input layer, which processes the integer-based word vector. Then we have an embedding layer whose output dimensionality is 16 as specified by the hyperparameters. And then we have a global average pooling layer. And finally, a fully connected layer before the output layer. So it's a simple feed-forward neural network model. So I have provided another example here that defines a bidirectional LSTM model. But in this example, let's actually go ahead and use the feed-forward model because it's slightly faster to train. So let's look at the model summary. And so here, this is just the base model without any graph regularization. And so here again, this is the summary of the model. And so we have about 160,000 trainable parameters for this model. And so we're going to be using this model as the base model to do graph regularization. And so let's go ahead and compile this model. And so one thing I want to mention here is that it's common for people to create a holdout set from the training distribution as a validation set. And the main idea is that you want to use the validation set in improving the performance of your model. As you're tuning your model, as you're trying to fix the model architecture, maybe you want to use a different number of neurons for a specific layer, or even just tune other hyperparameters. So validation split is typically used to improve the training of your model. And so that's why you want to use your training distribution and just hold out a small fraction of that for doing validation. And so here, because we started with 25,000 training examples, we take a fraction of the training examples and hold it out as validation. So in fact, here we're going to take things to an extreme. What we're going to do is we're just going to retain 10% of the 25,000 examples for training and hold out 90% for validation. So this is obviously not the ideal case because you want to use as many labeled examples as you can for training. But I just want to show that even when we have very limited labeled examples, we can end up learning a good graph regularized model. And so, I mean, when you're running experiments, feel free to reduce this value so that you have more labeled examples to train with. So in this case, we're just going to be training with 2,500 labeled examples. So I'll skip training the base model. We'll go ahead and train the graph regularized model directly. And so again, here we're going to use the feed-forward model for simplicity. And so again, as Cesar mentioned earlier, so wrapping an existing Keras model with graph regularization is really simple. As you can see, it just requires a few lines of code. So we define a graph regularization configuration object. So here you specify how many neighbors you want to do regularization with. Here we're using 2 neighbors. And then you specify the multiplier for the graph regularization loss term. And as I mentioned, this allows you to control the relative importance of this term with respect to the overall loss function. And finally, the distance metric that you want to use to compare neighbors. And so once you define this configuration, then you can use the graph regularization wrapper class that NSL provides to just wrap the given Keras model into a graph regularized model. So the output of this step is actually a subclass model in Keras that you can go ahead and train and evaluate just like you would with any other Keras model. So here again, we have used a subclass model wrapper for illustration, but NSL also supports functional API-based graph regularized models. So you can choose to use Keras layers to actually do the distance computation between embeddings, and our library provides APIs for you to customize it if you want. So let's go ahead and train the graph regularized model. So here we're training for 20 epochs. And so we are using a validation data set here, as I mentioned earlier. And so because we're using a validation data set, you do see metrics on the validation data set, validation loss, and the validation accuracy as well. And of course, we do have the scaled graph loss value being printed. It's scaled because this value already takes into account the graph regularization multiplier that we defined for this example. So while this is training, we're mostly at the end of this tutorial. I mean, I can take a couple of questions while this model is being trained. Let me switch back to chat to see if there's anything for me.
I don't think there are any open questions for you at the current time, Arjun.
Okay, thanks. So yeah, I mean, once the model is trained, I mean, then we can just go ahead and evaluate it. Everything else is really similar to a regular Keras model, and we just wanted to highlight here how to use. So to emphasize, the goal of this tutorial is to not demonstrate like near state-of-the-art performance on this dataset. We really wanted to show how you can do graph regularization when your input does not have a natural graph. So in this case, you just had a simple text-based dataset. And we use the notion of embeddings to convert them into to convert text into corresponding embeddings, and then build a similarity graph based on those embeddings using neurostructured learning. And then once you have a similarity graph, then you can do graph regularization with the similarity graph.
Arjun, there's a new question. Do you think we can generalize NSL to allow using the structure graph also at prediction time?
I see, that's a good question. So far we have only incorporated regularization during the course of training. So one thing that we wanted to keep in mind is that typically when people are building models and productionizing them, it's often complicated to make changes to the serving workflow. So, and we also want to keep the overhead of using neighbors to a minimum and such. So that's why we've sort of limited our focus to the training process. I'm not sure how you can additionally use neighbors at serving time. So yeah, I mean, for now, I think we don't have any plans of changing the serving workflow. So if you have any specific requirements or suggestions for how we can improve the serving workflow, I mean, please feel free to reach out to us either here or on GitHub later, and we can follow up more.
There's another question. Have you ever benchmarked this method to a full BERT-based sentiment classifier?
No, we haven't. As I mentioned, this is really a toy example just to illustrate the workflow for how to build a graph when you don't have a natural graph to begin with and then do graph regularization. The actual mileage of using a similarity graph really depends on the specific data set and the number of labeled examples that you have. And in general, it's in our experience, whenever you have an orthogonal source of similarity in your input, graph regularization tends to work much better in those contexts to improve model accuracy, as opposed to inferring similarity just based on the embeddings.
Okay, the next question is, can we evaluate the contribution of graph structure to overall model performance?
Yes, so that's well, in some sense, because we do have this graph loss term that's being printed here. I mean, and this will also show up on TensorBoard because it's a metric, and that allows you to show that shows you how much contribution to the loss term using the graph gives. And so if you have a good quality graph, then you can expect a strong contribution from this graph loss term. And again, as I mentioned, you can control the relative importance of the graph loss contribution to the overall loss function.
You also get an overall result, right? Because you have the base model that did not incorporate the neighbor information, and then you have the new model that included the graph-based regularization during training, and you can see the difference between the two, right?
Yep. Yeah, that's right.
So it's like an ablation study.
Yeah.
What is the impact of using structure graphs to represent sequential problems instead of more standard sequential classification approaches?
I think this question was asked earlier. Someone asked a question about this a sequence learning example where if examples in the same sequence can be classified as a subgraph, and then you can use edges to represent similarity. I'm not sure. I don't think we've done any experiment to see how the two approaches that the question mentions would fare against each other.
Okay, then Chun-Sung asks, by using graph structure, we can train the model even with limited labels, but still be able to use the information from neighbor nodes. So this is sort of semi-supervised learning. And yes, that's correct. Da-Cheng mentioned that in his introduction.
Yes, that's exactly right. So in fact, I'm going to show you a quick, so let me just quickly run the last two cells that we have in the Colab. So here we're just plotting the loss metrics and the accuracy metrics. So here, these curves are actually not the ideal curves that you want to see, but again, because we use very limited labeled examples, you don't get the smoothest of curves. But if you use more labeled examples, then you'll definitely get nicer curves. And so, and yeah, I mean, this brings me to the point. So this is really a perfect example of how you do semi-supervised learning. And because neural structure learning, and in particular graph regularization, allows you to leverage both labeled examples and unlabeled examples, because it can use the similarity between those two kinds of examples, it helps you compensate for the lack of labeled examples. And so using the graph really allows you to address limited supervision problems in a much better way than you would otherwise can. And so you can play around with the supervision ratio, like how many labeled examples that you want to use for training in your own example. And again, the mileage will vary based on your exact problem and data, but using the graph is certainly more information to the model than just using the labeled examples. And so yeah, the last cell just has some pre-computed values for different configurations. So I'll skip that, and that's it. We're at the end of this Colab tutorial. So that's all I had to present. And if there are any more questions, I'm happy to take them. We'll probably have a minute or so before we start the next.
I don't see any more questions, so maybe we should just move on to the next presentation.
Okay, sounds good. Thanks everyone. So in the next session, you're going to be looking at another aspect of neural structure learning called adversarial learning. And so here, the idea is to, instead of explicitly materializing neighbors from a graph, we will be synthesizing or dynamically generating adversarial examples to improve a model's robustness. And so you'll hear more about this from George. Stay tuned, and thanks for listening.
Thanks, Arjun. We can see your slides, George. Oops, they
Yeah,
just
one
went
sec.
away.
I needed to unmute myself.
Now your slides aren't there. Oh, okay. Gotcha.
I'm going to share them now,
Yeah.
Okay, cool. So everyone can see this, right?
Yep, there. We got it.
Okay. Thanks for the handoff, Arjun. So as Arjun mentioned, I'm going to be talking a little bit about adversarial regularization in NSL, and this is somewhat related to his previous talk in that we'll be synthesizing adversarial examples as pairs with our original examples to do the regularization. So our graph will basically be a bunch of vertex pairs where we have an original example and a linked adversarial example. And our adversarial example will weight the loss that we get on it to regularize the original model and use that to show how we can make a model more robust to these sorts of attacks. So first, we'll introduce some of the attacks that we'll use to regularize the model, and then we'll walk through a collab where we generate adversarial examples for a network on the MNIST dataset. So a quick refresher, this is an image from the introduction. Basically, at least in the image domain, an adversarial example is where you take an image such as this panda, and you add a little bit of directed crafted noise to it. And what happens is you get an image that is indistinguishable to human eyes, so it still looks like a panda to us, but for a network, it gets misclassified as a gibbon here. And so there are many different types of adversarial attacks out there, but here we'll focus on two iterative type adversaries. So the first adversary we'll look at is FGSM, which is the fast gradient sign method. This is one of the original attacks introduced in the literature, and it's a quick method to generate adversaries. So what this does is it takes a step in the direction that increases the loss of the network the most. So to find this direction, we basically take the gradient of the loss with respect to the input, and then we simply take a step in that direction. And to keep the actual perturbation to the image small, we clip that perturbation to some epsilon ball when we add it to our original input. And we'll show in the collab that for undefended models, we can already significantly degrade the accuracy using this. So the second adversary we'll take a look at is PGD, which is projected gradient descent. And this is considered as one of the strongest iterative first order attacks in the literature. So this is essentially an iterative application of the FGSM algorithm. And each step, we will calculate the gradient direction, just like in FGSM, and then we'll move in that direction. And if we exceed our epsilon ball bounds, then we'll project back to within the epsilon ball. And then we just continue and repeat to do that. So by taking multiple gradient steps, we'll get a better estimate of the true gradient direction than a single linear step. And so by doing this, we can produce stronger attacks, but we also have a much more expensive algorithm than FGSM. Because it's iterative, the cost scales with the number of iterations that you want to use. And so, as I mentioned earlier, these adversaries fit into the neural structured learning framework as a type of essentially synthesized graph neighbor for an image. So we take an input sample and we regularize it by including an adversarial loss, where we basically generate the adversarial neighbor, and then we calculate the loss for it, and then we sum the two losses to get our total regularized loss. So next, I'll take a look at an application of this to the MNIST network in this collab.
So if I could just interject for a second here, George, what that means is when you're doing adversarial regularization, none of the pre-processing work that I described for building the graph and packing the neighbors is required at all. So it's a much lower
that's
overhead.
Correct. Well, so it's correct that we don't have to build the graph in that sense, but we are building the graph in the sense that we need to construct the adversarial neighbor. And so as you'll see, depending on the algorithm you use, this could also be time consuming, and particularly in the case of PGD where it's iterative. But yeah, we don't need to do the sort of graph pre-processing.
Right.
that,
For the user,
was used earlier.
there's no explicit graph construction or packing that's required. The adversarial construction happens automatically within the NSL libraries.
Correct. Yeah. So can everyone see the collab right now?
Yes.
Yes. Okay, great. And just, were there any questions on like FGSM or PGD before I go ahead and go through this?
No, no questions.
Okay, great. Right. So I've gone ahead and run most of the cells in this collab ahead of time. If you'd like to follow along, you can. I'd recommend definitely using the GPU or TPU here. And in particular, adversarial training with PGD, that cell will take quite a bit of time to run, which is why I've gone ahead and done most of this beforehand. So in this collab, we'll do a couple things. First, we'll create a neural network as a base model, and we'll use the Keras API for that. And then second, we'll demonstrate generation of adversaries using both the adversarial regularization wrapper class and the add_gen neighbor function. So if you'd just like to generate adversaries against a model and you don't want to do the regularization, then you can use the add_gen neighbor function. And finally, we'll examine the performance of 3 models. So first, we'll look at the base model against just the regular test data set, against an FGSM perturbed data set, and a PGD perturbed data set. And we'll do the same examinations for the FGSM regularized model and the PGD regularized model. So the first step here is just to install the neural structure learning package, and then we'll import the necessary packages that we need. And next, we'll define all the hyperparameters that we need for this collab. So there are a couple sets of hyperparameters here. We have model-related hyperparameters, training and evaluation, and adversarial learning. And you'll see that a lot of these adversarial learning hyperparameters are fairly similar to how you would construct a synthesized graph. So first, for the model hyperparameters, since we're using MNIST for the input, each image is 28 by 28 pixels with 1 channel. So we'll have a 28 by 28 by 1 input shape down here. And then for classes, there are a total of 10 classes. Conv filters is going to be a list of numbers that specifies the number of filters in a convolutional layer. So we'll be using a convnet with 32 layers, and then 64, and then 64 layers again. The kernel size is the size of the 2D convolution window, and that'll be 3 by 3. We have a pooling size, which downscales the image in each max pooling layer, which is 2 by 2. And numFC units is the number of units in each fully connected layer. So we have a list of length 1. So we'll have 1 fully connected layer of 64 units. For training and evaluation, we have the batch size and number of epochs. So the batch size is 32, and we'll train for 5 epochs. And then finally, we have the adversarial learning hyperparameters. So the AV multiplier is the weight of the adversarial loss in the training objective relative to the label loss. So here we'll use 0.2. So for example, here multiplier 0.2 would be the original loss plus 0.2 times the loss from the adversarial neighbor that we generate. The step size is the magnitude of the adversarial perturbation. So this determines how large of a step we take for each gradient step. And we'll use a step of 0.01 here. So PGD iterations is the number of iterative steps to take when using PGD. And we'll use 40 iterations here. Oh, I skipped the grad norm. So the grad norm is the norm within which we measure the magnitude of the adversarial perturbation. So we'll be using the L infinity norm here, which is basically the maximum magnitude along any particular direction. The PGD epsilon is the bounds of the perturbation. So PGD will project back to this epsilon ball when we're generating the adversary, and we use a bound of 0.2. So in combination with the L infinity norm, this means that we can perturb any pixel by up to 0.2. And finally, we have clip value min and clip value max. So this clips the final adversary that is generated to make sure it's within the original domain bounds. So we'll normalize our pixel images to be within 0, 1. So we want to ensure that our final adversary is also clipped to within 0, 1. And so we'll be using the MNIST dataset here. And we'll load this from TensorFlow datasets. And we split into train and test. And we'll take these dictionary labels, which we'll need later to pass into the adversarial regularization class. And so as I mentioned earlier, we're going to normalize the pixels here to within 0, 1. And we'll also add 2 additional helper functions. So a convert to tuples, which converts our data set into an image and label pair, and a convert to dictionaries, which converts our image label pair into a dictionary where the key for the image is the string image, and the key for the label is a string label. And so for our train data set and our test data set, we will normalize. We'll shuffle for the train data set, but not for the test. And then we'll batch and we'll convert to tuples. And so next, we'll build our base model. No questions on the hyperparameters and data sets, right?
No questions so far.
Okay. So next, we'll build our base model, which, as I mentioned earlier, is going to be a convolutional neural network. And so in our hyperparameters, we had a length 3 list for the conv filters. So we'll have 3 convolutional layers. Then we'll flatten and have a fully connected layer, and then we'll output to the predictions. So here I'm not going to use the softmax activation, and so I'll just be returning the logits in the model. And the reason for this is if we were to take the softmax here, what would happen for a lot of these images is you'll get a vector, due to numerical issues, you'll get a vector that is essentially 1 for one of the classes and 0 or close to 0 for everything else. And that 1 messes up the gradient calculation in the adversarial generation, which means that you won't be able to get the adversaries that you want for regularization. So we build the model, and if we look at the summary here, so we have our input layer for the image, and then we have 3 convolutional layers of 32, 64, and 64 filters. Then we have a single fully connected layer with 64 units, and our final output layer, which is the logits for the 10 classes. And so if we train, and we'll use the Atom Optimizer here, sparse cross entropy loss, and since I'm returning the logits from the model, I'll pass from logits equals true here, and we'll take accuracy as the metrics. So we'll compile with these settings, and then we train on the training data set. And on GPU, it should be decently fast. So we're looking at roughly 13 seconds per epoch here. And final accuracy is around 99% on training. And on our test set, it's also around 99. It's 98.9%. And so next, we'll create 2 adversarially regularized models. We'll create one where we regularize with the FGSM attack. So this is a single step attack. And then the second one will regularize with PGD. So we'll need to make 2 adversarial regularization configs. So this first one is an FGSM config, and the second one is a PGD config. So most of the configuration here is similar, just a couple key differences here. So first, for the adversarial step size for FGSM, we pass in PGD epsilon here because we want to make sure both of these adversaries have the same perturbation budget. So we want FGSM to be able to move anywhere within the epsilon ball, the same epsilon ball that PGD will have. So that's why we set the step size to be PGD epsilon here. And since we take only one step for FGSM. For the grad norm, we're using the L infinity norm, and we make sure to clip within 0 and 1 for FGSM. And then for PGD, we have the same multiplier. The step size is now the step size that we specified earlier in the hyperparameters. So for every PGD step, we'll move 0.01. The grad norm is still on infinity. We have 40 iterations here, and we set the PGD epsilon to be PGD epsilon, so we clip to within that epsilon ball of 0.2. And then finally, we make sure that our final example is valid by clipping to within 0, 1. And so once we have these configs, building the actual adversarial regularized model is very simple. So first we create the same base model that we had before. So we create one for FGSM, and then we wrap it using nsl.keras.adversarial regularization. So this class, we wrap the base model. We need to pass the label keys for our input dictionaries, and we also need to pass the adversarial config that we defined earlier. And that's it for creating an adversarially regularized model. For PGD, we do the same thing. The only difference here is we pass in the PGD adversarial config. And we'll need dictionaries here for training. So we compile these with the same settings as the base model. We use the atom optimizer, we use cross entropy, and we take losses from the logits, and we have accuracy as a metric, and then we just train on the training set. And so this training set is the same training set that the original base model was trained on. So you don't need to actually provide the adversaries. The adversarial regularization class will generate them on the fly for you when it's doing training. And you'll get a bunch of warnings here, but you don't need to worry about these actually. So we'll train for 5 epochs again. It takes a little bit longer, it's around 16 seconds. And here's our training accuracy, and we also get our scaled adversarial loss. And so if we evaluate on just the standard test set, so there are no adversaries in the set, then we get around 99% accuracy. And we do the same for the PGD model. And as you'll see, this takes a lot longer to train due to the iterations that we have to take. So remember, this is 40 PGD iterations. So we're taking around 75 seconds per epoch here. And we get, at the end, we get training, evaluating on the test data set, we get around 98.9% accuracy. So all 3 models perform pretty well on the test set if we just take it as is and we don't do any perturbations to it. So next, we'll actually craft some perturbations on these test data sets and see how the models react to them. So to do this, we will set up an adversarial neighbor config, and this is going to be slightly different from the adversarial regularization config. The main difference here being that since we're only attacking the model and not regularizing it, we don't need the adversarial multiplier, and we don't need to wrap any sort of base model. So for the FGSM config, we pass in the L infinity norm. Again, the step size here is going to be PGD epsilon, and we'll clip to within 0 and 1. And we'll use a labeled loss function to provide the loss for each sample we pass in. And we want to calculate the gradient with respect to the input. We want to calculate the gradient of the loss function with respect to this input, which is why we need to provide this particular loss function. Again, we take the loss from the logits. And so now to actually generate these adversaries. So we're going to iterate through all batches in the test data set. And then for each batch, we're going to calculate the loss of the base model, as we'll be attacking the base model. We'll calculate the loss of the base model on the batch, and then we'll generate the adversarial example. So we can generate them by using this library function, generate adversarial neighbor. And it takes in the original input, the losses that we calculated up here, takes in the neighbor config, and then the tape which we use to watch this calculation. So we'll use that to calculate the gradient and add it to the original image. So after we've generated these images, we'll do a prediction on them, and then we'll update our accuracy metric here. And I'm also going to store these images for later use. So you don't need to do this. The actual adversarial example generation is just done in this highlighted section right here. But I'm actually going to store this for this collab so we can visualize them afterwards. And so the base model accuracy goes down to around 45%, and takes around 4.5 seconds wall time to generate an FGSM attack. So I'm going to go ahead and use this helper function here to visualize these images. And I've highlighted the examples that we get wrong with a red label. So for MNIST, since we're using 0.2 for the perturbation size, it's actually quite large, and at least to the human eye, we can see some of the perturbations here. But for more complex data sets such as SciFar or ImageNet, you can use a much smaller epsilon radius and get even better results. But even with these visible perturbations, most of these images should be still correctly classified to the human eye. So for example, if we look at this in the second row in the fourth column, we have what is a 6 here, and the base model classifies it as a 5 incorrectly. And so there are some perturbations here, but at least to the human eye, it's still very clearly a 6. And then again here for this 0, right underneath it, the base model misclassifies it as a 2. So we can see that the base model is already fairly vulnerable to the FGSM attack. And next, we're going to attack it again with PGD, which will be a stronger iterative adversary. So the only changes we need to the neighbor config here are we need to set the PGD epsilon to epsilon, and we need to set the number of iterations. And the step size is now the original step size that we defined in the hyperparameters. So when we're generating PGD adversaries, we additionally need to provide the model function to the generate adversarial neighbor function, and we need to provide the loss function that we need for calculating the gradient. So again, we have a very similar looking loop here. So we'll use this tape to calculate the loss on the first iteration, and again, we're attacking the base model here. And then to generate the adversarial examples, we'll pass in the original image, the losses that we calculated in the tape, the PGD neighbor config, and then we'll also pass in the model function, loss function, and labels. And so these will be used to calculate the gradient for successive iterations. And so the model function here is just our base model. So this will take in an input and give a prediction. And then a loss function is our standard Keras loss function. And then labels is going to be the set of labels for the batch that we're perturbing. So we generate a bunch of perturbed images here. And again, we'll do a prediction on these PGD images. And we'll update the accuracy metric. And so you can see this attack is much stronger here. The base model gets 1% accuracy and becomes completely unusable. And if we examine the images here in this first batch, we get pretty much every image wrong. I think there's one. So this 0 in the second row, third column is the only image that we perturbed and failed to have it be an incorrect classification. But every other image is incorrectly classified by the base model. So we've seen that the base model doesn't perform well at all against adversarial perturbations. So next we'll take a look at the FGSM regularized model and see how it performs. So again, setting up the attack is very similar. So the neighbor config here is actually unchanged, and the label loss function here is unchanged. The only difference here is in this adversarial generation loop. Inside this tape, we are going to take the loss with respect to the FGSM adversarially regularized model. And then we will generate adversaries against it and do the same updating of our accuracy metrics. So you can see that the model accuracy here is a lot better. It's 94.6%. And we're doing a lot better on our first batch here. So we get 3 wrong, but most of these predictions are now correct. And again, if we do this with PGD against the FGSM regularized model, so we have the same adversarial neighbor config set up as before. This time the model function is going to be the FGSM adversarial model, since we are attacking that model. And then the loss function is the same cross entropy loss function. So once again, in this label loss function section, we'll swap to a FGSM model. And we'll also predict with the FGSM model. And we'll see that our accuracy here is around 48%. So the FGSM regularization is strong against the FGSM attack. But if you use a stronger attack like PGD, it's still vulnerable to that. So we still get a sizable amount of incorrect classifications here.
But that's still a lot better than the 1% accuracy you got in the base model. So it's a pretty major improvement over the base model.
Right. So the base model is basically completely unusable with PGD at this kind of attack. But so FGSM does a lot better, but it's still pretty vulnerable. And so finally, we'll do the same thing, but with the PGD regularized model. So this neighbor config for FGSM is unchanged, and we'll use the same cross entropy loss function. When we're calculating the loss, we'll use PGD, the PGD adversarial model, and we'll also use it for prediction, of course. And we see that our base model accuracy is 96% here. So I think we get 2 wrong. We get 2 wrong in the first batch if we attack the PGD regularized model with FGSM. And then again, if we set up using PGD, so we swap the model function to be the PGD adversarially regularized model. We use the same loss function, and then we use the PGD adversarial model to calculate the labeled loss here, and we predict with the PGD adversarial model, and we get 94% or so accuracy. So the PGD regularized model is strong against both the PGD attack and the FGSM attack. So I think we get around 3 wrong here, yeah, this batch. So as we can see, there's kind of this gradient of attack strength here, where so the PGD regularized model is strong against all types, against FGSM and its stronger PGD variant. The FGSM regularized model is strong against FGSM, but not against PGD, and the base model is vulnerable to both types of attacks. And that's basically the conclusion of the collab here. So I have time to take questions if there are any. After this session, I think we'll have a short 10 or 15-minute break before we continue.
We actually probably only have time for a brief 2-minute break.
Oh man, okay.
Yeah,
so,
we're
no breaks for you
we're
guys,
running late because people have been asking all these great questions.
Yeah. So
those results are really impressive. I don't see any questions on the chat, so maybe we should just take a 2-minute break now. People can obviously ask questions during the 2-minute break, but we'll come back at like 11:36 Pacific time in 2 minutes. that sound okay to everyone?
Yep, sounds good. I think there's a question on chat. It's not related to adversarial regularization though. What is the strength and weakness of graph regularization compared to graph convolutional neural network and its variants? Can we apply graph regularization on models to do inductive learning instead of just transductive learning? And what is the future research direction for graph regularization? I can take that. Thanks for the question, Chun-Liang. So we'll be actually talking more about the future of not just graph regularization, but also NSL in the session after the immediately following session. So we will talk more about graph regularization and also graph convolutional networks and what the differences are. And in fact, we'll also show you how you can build a graph convolutional neural network using the neural structured learning framework. So just stay tuned to hear more about that. Okay, I think let's get started with the next session. I think I'm up next. Okay, I'm going to be a bit quick on this one because we're low on time. So hi everyone, it's me Arjun Gopalan again, and so I'm going to be talking to you about how to use neural structured learning in TensorFlow Extended. And so in the previous sessions, you looked at how to do both graph and adversarial regularization with regular TensorFlow. And so in this session, we'll be looking at how to extend that usage to use neural structured learning in the context of TensorFlow Extended or TFX. So before we get started with that, I want to motivate the need for us to discuss this topic. So typically when people try to frame new problems as machine learning problems, they tend to focus most of their efforts and time on how to model that problem as a machine learning problem and what kind of neural network architecture they may want to build, what kind of hyperparameters they want to use, and so on and so forth. And so this can be thought of as the modeling phase of the problem. And it's certainly the right one to do essentially as you, especially when you start working on a new problem, because you want to be able to quickly prototype a solution to see if there's any promise. And so it makes sense to focus on just the modeling aspect of the solution. But this is certainly not the be all end all of a typical machine learning pipeline. In fact, to put a machine learning pipeline in production, there are a lot of other tasks that need to be in place. And in fact, as you can see, the modeling phase at the center in yellow represents a relatively smaller fraction of the overall tasks that are required. And so here, I've listed a few of these tasks that may be necessary in a production machine learning pipeline. So obviously, there's a lot of effort that's typically spent in just collecting the right data that you want to train your model. And once you collect your data, you may want to make sure that your data has no anomalies to make sure that all the examples have the right features that you need for your model. And so then you can do things like feature engineering. Maybe you want to distill the set of features that you have into a smaller set that your model consumes. Maybe you want to do some transformation of features in your examples, and so on and so forth. So there's a lot of pre-processing work that typically needs to be done before you actually get to training the model. And so once once you do that, then you're in a position to actually train your model. And so once you train your model, you want to make sure that you validate the model against a holdout set to make sure that it's doing reasonably well on unseen data. And this is something that's important because you don't want to publish a model to the serving infrastructure side before validating its quality. And so the model validation is an important aspect of a production machine learning pipeline. And of course, if all of this if you have distributed resources in your environment, and then they just introduce a whole new level of complexity, and you want to be able to leverage those resources to handle large scale workloads. And so what is really TFX? So TFX is a production scale machine learning platform that's based on TensorFlow. And so primarily it serves to handle what we call ML ops. And so many of you are familiar with the canonical DevOps, which are used for managing operations in developer environments. But ML ops is kind of the equivalent to automate, manage, and audit machine learning workflows. So we just looked at some of the tasks that may be involved in a typical production machine learning pipeline. So you have things ranging from data preparation and analysis to model training, evaluation, and finally to model deployment before you can serve it to do inference. And TFX allows you to orchestrate all of these workflows using platforms like Apache Airflow, Apache Beam, and Kubeflow pipelines as well. And so TFX is what I'm going to be describing to you is the open source version of what Google uses internally for production scale machine learning. So it's used across a wide variety of teams and services in Google. So now that we understand what TFX is, let's dive into a little more detail on how you would build a TFX pipeline. So TFX comes with a number of off-the-shelf, what we call components. And so you can think of a component having a dedicated purpose in the pipeline. So it essentially takes some input, does some processing, and spits out some output. And so these off-the-shelf components are categorized across a number of categories, starting from the left all the way to the right. We'll briefly look at them one by one. So you start off with data ingestion. And so this is the first phase in your pipeline where you load examples from storage into your pipeline. So we have the example gen component for that. And then you have data validation. And so here you may want to compute statistics on the features in your input data set. And then you can also define a schema for your data set. You specify what features you want to use, what their range of values are, and so on and so forth. And you can use this to actually do validation to make sure that there are no anomalous examples or examples containing values that are out of the distribution that you may expect for certain features. So once you validate your data, then you can do feature engineering. So here we have this transform component, and that allows you to do feature transformation. And so an example is you can convert variable length text data to a fixed length to fixed length representation, or you may even want to convert text-based representation into the corresponding integer word vectors, and you may want to do things like normalization of numerical features in your input. So all of this can be done in this transform TFX component. And so once we have all of the features that are ready to be consumed by the model, then we can actually go ahead and implement our model trainer. And so here you can think of using estimator or keras to build your model. And once you train your model, as I mentioned earlier, you want to evaluate the model against some holdout unseen data to make sure that it does reasonably well. And then you also want to validate it so that you don't publish a model that doesn't meet your metrics. So you may want to set a bar on your metrics, say achieve a target accuracy of 90% or other metrics. The model validator allows you to specify those parameters, and once the model meets all of those quality metrics, you can go ahead and deploy this model for model serving. And so the pusher component allows you to publish a trained model for serving, and finally the model server model allows you to actually serve the model to do inference. And so TFX is a comprehensive ecosystem, and we don't have a lot of time to talk more about TFX. There's more information on the TFX website, as well as tutorials that you can look at. And I'm certainly no expert on TFX myself, so I just wanted to give you some context on what TFX is before we talk about how to use neural structured learning in the context of a TFX pipeline. So hopefully this sets some context for what we're going to talk about next. So to recap, regularization in NSL is of two kinds. So we have graph regularization first, and then adversarial regularization as the other aspect. So for graph regularization, we require two data pre-processing steps. So first is building a similarity graph if your input does not already contain a natural graph. Second step is to use the similarity graph to create what we call the augmented training dataset. And again, as to recall, the augmented training dataset includes the features of the original examples, as well as the features of the neighbors from the similarity graph. And once we have these augmented examples, then we can regularize the model training using these neighbors from the graph. On the other hand, adversarial regularization does not require any data pre-processing. So in this case, adversarial examples are dynamically generated during the course of training. And the main idea here is to improve the robustness of a model to make sure that it's robust to malicious attacks. So the key distinction between these two paradigms is that once the objective of graph regularization is more to improve the accuracy, while the objective of adversarial regularization is to improve the robustness of the model. And graph regularization requires some data preprocessing, while adversarial regularization does not. So we'll look at graph regularization first and see what it takes to build a TFX pipeline of graph regularization. So if you recall the off-the-shelf components in TFX that we just looked at, you'll see that the data preprocessing task for graph regularization, in particular graph building and training data augmentation, don't necessarily map onto those off-the-shelf components. So we can't just use those components in building our pipeline. However, TFX defines, supports the definition of custom components. And so a custom component is essentially a Python function where you specify what the input and output signatures are, and you get to implement some arbitrary computation within this component. And then you can define multiple components, multiple custom components. You can wire them together, and you can also wire them with other off-the-shelf components to build a more comprehensive TFX pipeline. And so this abstraction is really powerful, and we'll see how we can use them to build a fairly flexible and easy to reason about pipeline shortly. And so let's revisit the example that we looked at earlier for simplicity. So we have the sentiment classification example where the task is to classify text-based movie reviews as good or bad. And so the workflow for a graph regularized model for this task is to start out with the text-based movie reviews. Then we convert them into corresponding embeddings using a pre-trained model on TensorFlow Hub. And then we use the graph builder from NSL to build a similarity graph based on those embeddings. Once we have a similarity graph, we create an augmented training data set using the features of the original movie reviews and the features of the neighbors from the similarity graph to create an augmented training data set, which is finally passed to the graph regularized model trainer. So I've added a link to a full end-to-end working Colab tutorial that illustrates this workflow in the context of a TFX pipeline. We're not going to have time to go through this Colab. I hope you get a chance to experiment with it at your own pace later. But I just want to give you a high-level schematic of what the pipeline looks like for this example. And so in this diagram, the orange boxes represent off-the-shelf TFX components, and the pink boxes represent custom components that we built for this example. So we started with the example gen, which is the first phase in the pipeline. You read input examples from storage into your pipeline. So in this case, we have the text and the label as two features. Then we have the identify examples custom component. And this custom component assigns a unique identifier to each example in our data set. Once we do that, we have a set of off-the-shelf TFX components in our pipeline. So we have statistics gen to compute statistics, schema gen that generates the schema, an example validator that validates the examples to make sure that it doesn't have any anomalous instances, and the transform component that transforms the example. So in this case, it can convert variable length text into a fixed length representation, and also convert the text-based representation into integer-based word vectors. So recall that for graph regularization, we need two ingredients. So one is a similarity graph, and the other is an augmented training data set. And so far, we haven't prepared either of those inputs. And so first, we build a graph based on our input examples. So we take the output of the identify examples component and pass it to a custom component that we call synthesize graph. And this custom component does two things. So it takes the text in the movie reviews and converts them into corresponding embeddings using a pre-trained model on TensorFlow Hub, and then uses these embeddings to build a similarity graph. And the output of this component is what we call a graph artifact. And so this similarity graph artifact combined with the transformed examples are passed through a graph augmentation custom component that does the training data augmentation for graph regularization. So the last step is, of course, just to do simple graph regularization as we saw earlier in the trainer component. So switching gears, on the other hand, adversarial regularization does not require any data preprocessing. So your TFX pipeline will remain largely unchanged. So all of the off-the-shelf TFX components work just fine. Just a change in the trainer component is what is required to wrap your existing model with the adversarial regularization API. And so this typically just involves a few lines of extra code to convert your existing model to an adversarially trained model. And as you can see, adversarial regularization is a lot simpler to incorporate into TFX as it does not require any data preprocessing. But again, as I mentioned, the objective here is to improve the robustness of a model, while graph regularization tries to improve the accuracy of the model. And that's all I had to say for this session. We're running low on time, so unless there are pressing questions, maybe we should move on to the next session, and we can probably combine questions towards the end of the session.
Yeah, there are no outstanding questions, Arjun. Thanks.
Okay, thanks. So yeah, so next we'll be looking at some research and future directions in NSL. Over to you, Chun-Ta and Phil.
Right. Can you guys see my screen?
Yep.
Yes, we can.
Right. Thanks, Arjun, for presenting how we can use neural structure learning in KFX. And in the following section, we will switch gear a little bit, and I will be short. Basically, Phil and I will present some research works that are built on top of neural structure learning. First, so we will show how we can use graph regularization to help improve the image semantic embedding learning. And this is a research work published in Wisdom 2020. So first, what is image semantic embedding? Actually, it's a dense representation capture semantics, which tells whether two images are similar or not in terms of the semantic. For example, these are two bridge images. If we simply compare them pixel by pixel, the similarity may not be high, but from human perception, we consider these two images to be similar in terms of semantics. And if the user type in, like, if we want to identify the instant label of a semantic, for example, given a query like Golden Gate Bridge, then we want to identify whether this image are Golden Gate Bridge or not, compared to the other image on the left side. And we call this is instant label granularity or ultra-fine grain semantics. So from human perception, it's not easy to capture such ultra-fine grain semantics, but from human perception, it's easy. But learning such embedding for machines is a challenging task, partly due to the large variance seen among the images that belong to the same category or class. So even though it's challenging, it's a core of many modern image-related applications, such as image search, or either you can query by keywords or query by example images. In this work, we aim to learn an image embedding model that can capture the nuance of the image semantics at ultra-fine grain level. And this is our neural architectures used to learn such image embedding. If we ignore the button health part, then it's just a regular image classification model. And if we consider the flow in red on the button health, and basically is to add a graph regularization in order to improve the model performance. I believe you think it's quite familiar. Actually, this is exactly the same workflow we introduce again and again in this tutorial. Since we focus on the neural structure learning, so we will ignore some techniques such as sample submix used to train the model. If you are interested, please refer to our paper. So let's join in the structure part. So basically, the graph or structure here is built from the co-occurrence signals. Essentially, this is to answer the following question. Given that one image is selected, what are the other images that are sufficiently similar or will be selected? Say the query is white English bulldog, and if two images are co-occurred by many times, then we can add an edge between these two images and making them as neighbors in the graph as shown in the left figure here. And this co-occurrence graph is used to regularize the training of the embedding model, such as embedding can capture the semantic closer to human perception, because we are actually using some human reactions to construct such co-occurrence graph. Here are some experimental results. For each query image, we provide the top 3 nearest neighbors retrieved from an index of 1 billion images based on the learned image semantic embeddings. So the image colors by green are rated as highly strongly similar with the query image, and the images highlighted or colored by red are not similar. from this example, we can see that if the query image is a white score, then the other white scores can be correctly retrieved by using the embedding learned from neural structure learning. And the other examples are like race car sofa, and using neural structure learning actually can retrieve more similar images compared to other methods. And next, I would like to discuss some challenges when applying the graph regression to the cases where there are very few label examples or given the graphs are noisy. In this new 2019 paper, we propose graph regularization models that address these challenges. It basically consists of two components: an agreement model that predicts the probability of two connected nodes having the same label, and a classification model that predicts the node labels. Actually, the agreement model is helped to remove the noisy edges when we apply graph regression. So basically, the agreement probability will be applied as an edge weight in the graph regularization. And after learning the classification model, we can add the most confident samples, unlabeled samples to the training dataset, such that we can enlarge the training data. Basically, the agreement model takes a pair of connected nodes as an input and predict the probability whether they agree or not. And the agreement is based on the node labels. And because the agreement probability will be low when two nodes does not carry the same labels, so we can consider adding this learned agreement weight as a edge weight in the graph regression. So this is basically an overview of this work, and it consists of three main steps. One is that we can train an agreement model using the label examples and with connected nodes. And then we can train a classification model with the graph regression with the learned edge weights. And in the last step, we can further extend the training data set by using the most confident predictions. So next, Phil will introduce the techniques beyond graph regression. Phil?
Give me a second. Okay. Right. So we've heard a lot. So I'm Phil. We've heard a lot about graph regularization already, and how we can use the relationship between examples to improve model quality and work with semi-supervised data. So in our current implementation, the graph regularization is a relatively simple idea. In our current implementation, it can be applied to any graph, and its simplicity has an advantage that it's very scalable. It just extracts small subgraphs that and neighbors in particular, and it makes it easy just to apply to any generic graph you have. But in doing that, we throw away a lot of information. Like if we were interested in classifying, say, node 11 here, there's other information about the graph that we are losing. Like we wouldn't know that neighbors 7 and 9 are related through node 8, or that there's node 3 that's more than one hop away. So we think that this information might help us complete our task better, which might be node classifications. So one way to do this naturally to incorporate the structure in graph regularization is to reformulate graph regularization as a GNN. And in particular, we can do that using the message passing framework introduced in neural message passing for quantum chemistry. So say we were interested in node X, we could aggregate. So we would look in a message passing phase, we would look at the neighbors of node X, and we'd aggregate, we'd calculate the distance between X and its neighbors, and then we'd aggregate it all together in some permutation invariant way. So now we have a message associated with the node we're interested in classifying. And in our readout phase, we end up normalizing by the weighted degree of the graph, and that gives us what we have been calling a graph loss or graph regularization loss. So graph regularization then in this manner is just a GNN. If you imagine that a graph neural network as being a function that takes a graph and outputs a graph of the same topology. So, and in doing so, it updates the hidden states associated with each node and edge and the global graph state. So in the case of graph regularization, where the edge state is the distance between the similarity metric between the sender and receiver, which would be KL divergence, L2 distance. And then we aggregate all those pairwise distances to attain the graph regularization loss, which is the graph state. And so doing this framework will just let us do computation over arbitrary graphs. It no longer needs to be a star graph where you have just a node and its neighbors. So in a little more detail, this slide's maybe a little heavy. We can use graph regularization by we implement it with GraphNets. So so DeepMind has a framework they introduced in a paper called Relational Inductive Biases, Deep Learning and Graph Networks. And we chose to use GraphNets to handle our message passing. So the framework breaks up the computation into 3 blocks: the edge block, global block. In graph regularization, it's the edge block that is calculating the similarity from the senders and receivers. So V is the vertices, and E is the edge weight. And from that, you can calculate the similarity metric. Node block would be skipped, and then you just get the global block to aggregate all those distances and kind of compute a graph regularization loss. And so this all works by inside Keras, right? So you node classifier would just be a generic Keras model that classifies a single node, and a graph regularization model is another Keras model that is using the machinery of GraphNets to handle the message passing based on what you pass the graph regularization configuration. And then after that, you just compile, fit, pass the Keras optimizer, Keras loss, and the trained data set will need to produce batches of graphs, and we plan to provide utilities that help you do that. And so, of course, the advantage of reformulating graph regularization as a graph neural network is that we can try other graph neural networks. So here's an example of a graph convolutional network with graph neural networks with GraphNets. So edge models, encoder models, node models, these are just Keras layers. And then you pass them to these GraphNets modules that handle all the message passing based on these Keras layers. And so this is the API is very similar to just subclassing a Keras model, except you wire it together using the machinery of graph nets. And so we plan to provide some prepackaged versions of this, like graph convolution networks, graph attention networks. But of course, users are more than capable of doing it themselves. And once you have this graph convolutional node classifier, this is just a drop-in replacement for a graph regularization model. And you can easily try different types of graph neural networks as well as graph regularization. Yeah, so that's all I have. I'll hand it back to Da-Cheng to summarize the story.
Okay, thanks, Phil. So summary. So I hope all of you enjoyed the hands-on collab and tutorials today. So to recap, training with structured signals is very useful. So last label data are required to train a model because of leveraging structured signals. Also, learning with structured signals leads to models that are more robust to small, malicious perturbations. So neural structure learning provides APIs, libraries, and also standalone tools for learning with structured signals. So throughout this tutorial, we provide step-by-step hands-on collabs to guide you about the concept and the best practice of using neural structure learning. And finally, the neural structure learning works for all types of neural nets, so feed-forward, convolution, and also recurrent neural net. So we also want to mention collaborations are highly welcome. No matter you are interested in library and system design, or you are interested in conducting research related to neural structure learning, please do file a GitHub issue and talk to us. We will be looking forward to the opportunity working with you folks. Finally, we summarize all the pointers in these slides. You can learn tools, libraries, and hands-on collabs in detail at our website. And please also star our GitHub. We do take and respond to the GitHub issues, and we are looking forward to developing this framework with all of you. Together, let's make this framework more comprehensive, and we will be waiting for you, waiting for your pull request on GitHub. And thank you very much. So we are slightly over time, and let's take one or two more questions if there's any.
I just want to mention that in case people have questions later during the course of the week, you can send messages on vFairs, and we'll monitor them from time to time and try and answer them. And like Da-Cheng mentioned, GitHub is always available for you to reach out to us. And if you have more specific requirements on your use case, or if you have any feedback for us, please fill the feedback form that Da-Cheng has presented on his slide.
Cool. So with that, thank you very much. Let's conclude this tutorial. Thanks, everyone.
Thanks, everyone.
Thank you.
Yeah, thank you.
I'm going to stop recording.